I officially open this international conference on Thermofluid 11 2020. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much to Mr. Wasis Wildan for the opening speech and for opening this conference. And lastly, before we start the conference and start the presentations from the speakers, we would like to invite you to watch an introduction video about the Mechanical Engineering and Industrial Engineering Department of Universitas Gadjah Mada. So to the committee, if you could play the video, please do. Thank you very much.
Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditation. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology. Over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever.
Okay, good morning, ladies and gentlemen. I hope you are still with us. I've just been informed by the committee that Professor Samsul and the other speakers as well are still, as well as the committee, are doing final checks for the presentation to make sure that everything is going to go well, etc. And before we go to them, I would just like to remind you about today's agenda one more time. So in today's agenda, of course, this event will consist of 2 days, but for this particular day, there will be 3 presentations from 3 different keynote speakers. And the first keynote speaker is Professor Sutrisno from Universitas Gadjah Mada. And afterwards, followed by Professor Graham Gus Nathan from the University of Adelaide. And lastly, Professor Wolfgang Polifka from TU Munich. And of course, alongside those presentations from the keynote speakers, we'll also have exciting and amazing paper presentations with various themes from a number of academics and researchers, of course, that encompass several topics surrounding the thermofluid engineering topic. And they will also not only be from Indonesia, but as well as other countries, researchers from other countries will also be participating. So again, there are certainly plenty to look forward to during this conference, and I would like to invite you to stay with us until the end, because of course, there are going to be a lot of excitements. And for your information, this year's Thermofluid is conducted in a very unique circumstances. The committee, as well as the other components, including Universitas Gadjah Mada, had to adapt to the current situations in order to be able to conduct this conference and hold this conference. And of course, it took the combination and teamwork of a lot of people and a lot of creative individuals behind this. So to the committee and everyone that's involved in the making of this conference in this particular year, we would like to say thank you to each and every one of you, because of course through your hard work and dedication, the 11th International Conference on Thermofluids can be conducted, albeit with different circumstances and different measures as well as procedures. And I am still being informed by the committee that they are still doing the final checks to make sure that the presenters will be able to present their papers and their presentations well. So I invite you to please hang with us a little bit more, and we will come back to you in a very short time. Thank you very much. Okay, we already have Professor Samsul with us because in this next session, we will have keynote presentations from Professor Sutrisno and Professor Gragus Nathan. And this particular session will be moderated by Professor Samsul Kamal from Universitas Gadjah Mada. So to Professor Samsul, the stage is yours. Thank you very much.
Okay. Thank you very much for Fikri. All right, so first of all, I think I would say good morning to you all, ladies and gentlemen, and then especially we are gathering in the very prestigious event that is 11th International Conference on Thermofluid 2020. I think, as mentioned before, that although we are still struggling in, let's say, suffering for COVID-19, but thank you, God bless to you all, to us, and then because we are still can conduct this conference can be conducted in Yogyakarta especially. And then I think this conference is very important because although we are, as I said before, that we are still suffering in such a pandemic, we said, but the science must go on. I mean, at this moment, the 11th Thermofluid can be conducted, should be all right. Okay, I think first of all, I will introduce you the two person very, I think, very famous. The first one is Professor Insinyur Sutrisno, MSME PhD, IPM ASEAN ANGS, that is the staff from the Mechanical and Industrial Engineering Gadjah Mada University. Right. Professor Sutrisno first graduated from Gadjah Mada University, 90, I think, yeah. And then got master from America, that is the University of Colorado. And then his doctoral degree, that is from University of Colorado as well. Right. And then he especially doing many research on aerodynamic, something like that. And then he is interested in many topic. I think all of these topics about especially in aerodynamic. And then the professional organization of forces, call it PII, Persatuan Insinyur Indonesia as well. He is also a member of Komisaris in Ikatan Ahli Teknik Otomotif atau or IA2. Right. Okay, I think that's for Professor Sutrisno. So please, we invite you, Professor Sutrisno, to give your speech in this very prestigious occasion. So the time is for you, Professor Sutrisno.
Thank you very much. I would like to start my presentation. And the aerodynamics of aircraft fighters with canards. So the aerodynamics of aircraft fighters with canards. The presentation going to be start with introduction, experimental methods, result discussion, and conclusion. So aerodynamic fighter is very interesting because it requires a very large defense investment to defend national sovereignty, security, political and military strategies. And in this presentation, we try to show the experimental method we use. One, using water tunnel, the only water tunnel in Indonesia, I believe. And secondly, the model in CFD. We deal with several fighter aircraft that use canard, such as Sukhoi Su-30.
I'm sorry, Professor
Sukhoi...
Sutrisno. Professor Sutrisno, can you hear me?
Yeah.
I believe that you haven't shared your screen to us, so apologies. I was wondering if you could share your presentation to us because it hasn't showed up on our screens here.
Okay. How about now?
Okay, I can see your screen. Just head on straight to your presentation. Yep, it's pretty clear from here. Please continue, sir. Apologies. Thank you very much.
Thank you. And this is the topic, the aerodynamics of aircraft fighters with canard. First of all, we'd like to introduce our experimental methods. One, using water tunnel. I believe it's the only in Indonesia, I believe. And model in CFD. We start to talk about several fighter aircraft that use canard. Some of our research in Sukhoi Su-30, Sukhoi Su-47 Berkut, Eurofighter Typhoon TP1000, Chengdu G10, Rafale Gripen, and SBTF fighters. First of all, for the case one, I present only some of them related with Sukhoi Su-77 Berkut and Eurofighter Typhoon. Flow visualization and performance investigation using gamma water tunnel. We believe that Su-47, with its front swept wing, look like this one, have two vortex cores. One is because of the front swept wing and vortex cores, and the other one coming from the canard, while the Typhoon only was one vortex core as shown here. So, and then therefore, SU-47 has greater lift coefficient, gave rise to the abrupt lift change. It has a shorter takeoff, a lower minimum flight speed, and minimum landing distance. So it looked like that. This is the comparison between aircraft that have forward swept wing and the other one have delta wing. This is the forward swept wing and this is the delta wing. We use water tunnel, so this is the result. At last we found out the graph for the vortex breakdown location. This is the comparison between Sukhoi and Eurofighter. And this is the comparison between the lift coefficient of Su-47 and the Typhoon. And this is the comparison between those drag coefficients. At last, we can summarize that Su-47 have two roll-up vortices, two vortex that induce lift coefficient. The Typhoon has only one vortex, while in the other way, 47 has greater lift coefficient that give rise to the abrupt lift change. The front swept wing mean improved stability at high angle of attack. This is the result. Sukhoi Berkrot plane stall occur at angle of attack 50 degrees, while the Eurofighter Typhoon stall occurred at 45 degrees angle of attack. Now we go to the case 2, the numerical studies of the flow around Eurofighter Typhoon like fighter aircraft, but on subsonic speed. In this result, we show the CL, lift coefficient, drag coefficient, CL to CD with respect to the angle of attack, the graph of axial speed change along the wing, and Carnot vortex. It also shows the graph of the wing and Carnot vortex at different angle of attack, including surface pressure contour on the fuselage. We show also the graph of the pressure coefficient at 30% and 60% root wing core. You will see here that the graph of, we can show the graph of CP distribution along the span of 30% and 60% wing core that presented on figure 5 here. This is 30% wing core, and this is the 60% wing core. So here we see the pressure coefficient at location at 30% core and 60% wing core. Here we can show the presence of the suction area and suction peak value. Case number 3. This is the result that we proud of because we can show something related with Sukhoi Su-30. This is the vortex dynamic study of the canard deflection angle influence on the Sukhoi Su-30 like model to improve stall delay at high angle of attack. So something we want to show you is something related to Pugachev Cobra. It's a maneuver that up to now is not defeated yet in the world. The pilot usually chasing one another in dogfighting, and the first pilot movement try to avoid enemy that chase them, and Therefore, they try to switch the chaser. The chase one become the chaser using the maneuver of Pugachev Cobra. The movement usually use mechanism to lift the nose up to a very high angle of attack at low speed. It reduce speed, and therefore the chaser began to overspeed, and the chase one become the chaser, and then return to the normal flight position. And canard deflection on an extra high angle of attack produce a high CL. Can be used Pugachev Cobra like the one to show you here. Here we go. This is Sukhoi. It has a very high angle of attack, and the lift is still so big. So you will see here, it can angle of attack become higher than 90 degrees. So this one is actually the picture of Sukhoi, and we use and computer CFD, but also water tunnel. This is the model used in the water tunnel. In this, the model we got it in CFD. So we'll see here how clever they is because the big head of the Sukhoi and the head of the Sukhoi become an airfoil type movement. So therefore, the vortex merging here, bending around that create a high lift on the head. So this is the result of the water tunnel calculation. This is the angle of attack from 10, 20, 30, 40, 50, 60, up to 80 degrees angle of attack. And here is the lift coefficient. The lift coefficient at the low angle of attack, it looked like this one. This is the wing having a low angle of attack, and this one is the canard straight on the same line. This is the picture in around here, where the wing angle of attack is very high, something like 80 to 90 degrees. And this is the canard that is deflected 40 degrees. So the something that is very good from the design of Sukhoi is in this part. Usually, after it's tall, the lift is going down so fast. But at Sukhoi, there is something very good happen. Well, there is no effect of canard at low angle of attack, but at high angle of attack, here is for around 40 degrees. The angle of attack of the canard deflection create the high lift, especially for high deflection. Here is go when it becomes 40 degrees of canard deflection, the CL is still very big. And another thing, the result that I also figure out even further is the comparison between several fighter, Chengdu G10, Eurofighter Typhoon TP-1000, Rafale from France, Sukhoi Su-30, and Gripen. And here is the comparison. How about the location and the deflection of the canard, and then the main wing, and then the engine intake. By side, if you can figure out in more detail when looking down at the table that Sukhoi have a very good result. So this is something that good to discuss. The canard will affect the aerodynamic character in water tunnel or in CFD. The change of canard deflection angle will affect eddy nuclei and then flow interaction, lift force coefficient, vortex breakdown, also location and pressure distribution. So actually we can figure out what happened at low angle of attack and at very high angle of attack. When at 40 degrees, actually there is no difference between the effect of the canard deflection, so it's not recommended. And at 40 degrees, when angle of attack become very high, the use of canard deflection will improve slower decrease in coefficient of lift. And then at very high angle of attack, higher than 60 degrees, even up to 80 degrees. In our measurement, the deflection angle of 30 degrees to 40 degrees still capable to delay the occurrence of stall. That's what happened to what we call it Ugasev Cobra, sorry. And case number 4, straight body type fuselage. It looks like here's one here. We use CFD simulation. Here is the wing, and this is the canard. And the fuselage look like this one. We will see here the use of key criterion, something that we use it so much because it can probe vortices. You can see the vortex very clearly using key criterion, the location grid to emphasize the micrograding effect of the turbulent boundary layer. Basically, using all of these methods, we can show the detailed quantitative velocity, pressure, trajectory of the vortex core, wing, negative surface pressure distribution, and will provide you with a clear picture of the opportunity for performance improvement. Something like what to do with better lift, what to do with agility and maneuver ability if you want to give a new design, better design. So here is the result. This is the effect of canard location and deflection. This is the canard location, this is the wing. So basically, the canard above the main wing here. And the canard is deflected so that the wind that straight from the front deflected by the canard and go down here. But usually, because the canard is not aligned with the wing, therefore the vortex streamline deflected and from canard to the main wing. So that is here. Here I think there is some distance between the main wing and the wing. So basically, because of the distance, the lift coefficient reduce. This is the result for canard location and deflection. And something that is very important too is related with the vertical wall in the side. On the left and on the right, there is a vertical wall. This vertical wall usually close to the wall, uh, the pressure due to within become negative surface pressure distribution. And when it is in the vertical wall, so it's useless. So basically, because of negative surface pressure distribution at the vertical wall, usually wasting amount of energy because it doesn't produce lift due to the vertical wall and near the canard and near the wing. Once again, try to emphasize that key criterion algorithm will give you the complete picture of the vortex dynamic mechanism. And secondly, the trajectory of the vortex course gradually move away from the wing surface and reduce the CL. So actually, it is recommended that agility, maneuverability improvement include the combination system of constituent device of different style. We are trying to emphasize what is blended wing body design. This one is the result because the body is circle. But if we use blended wall, it look like the wing. This become the negative pressure become very good lift here. So it's going to be very good if the fuselage has a blended wing design body. The body is flat, therefore gives significant CL. And therefore, here, modifications such as blended wing body design and alteration of single to double engine, because there are some fighter having only one engine, and there are some fighter having double engine. Therefore, there is some benefit of to deliver more power and reduce the effect of the bomb. And here is the conclusion of our study. It means that key criterion, it's very good to prophylaxis. You will be able to see the vortex very clearly. And you have a detailed quantitative velocity, pressure trajectory of the vortex core, wing negative surface pressure distribution, and give you clear picture the performance improvement. So basically, we go successful to combine between design of Sukhoi and the Gripen. At last, the lift coefficient it's higher theoretically better than Sukhoi. And secondly, negative as surface pressure difference at vertical wall usually happen at near the main wing or near the canard. It's become the very bad. It's very good if the body become blended. So at last we can figure out that Sukhoi Su-30 to improve stall delay at high angle of attack, they can change the chaser become the chased using a maneuver like Pugachev Cobra. Actually, they lift the nose up to a very high angle of attack until 190 degrees with a low speed because it reduced speed. And at last, the chaser become to overshoot and return, and the chase can return to the flow speed using Pugachev Cobra. And we can prove that at angle of attack much higher than 60 degrees, with deflection angle between 30 to 40 degrees for the canard, we can able to delay the stall up to 80 to 90 degrees. This is what of my presentation about the aerodynamics of the fighter with the canard. Thank you very much, and come back to you, Professor Samsul.
Okay, thank you very much, Professor Sutrisno. All right, so it's very great presentation. I think it is also very important thing because as we know that each country now is trying to be superior. And then I think it's your presentation give us very important technical thing to be considered. Okay, I think give Professor Sutrisno applause. It's very good. Okay. Thank you very much again, Professor Sutrisno, for your presentation. And then now I will invite our honorable guest from Australia. Say, yes, please, Professor Graham Gus Jonathan. Would you please on the screen? It's already there. Hello, Professor.
Yes, hello. Can you hear me?
Okay, yeah, that's great. So you're already there then. Okay, thank you very much for your, okay, you can come to this prestigious event, I think. Thank you very much. And then, first of all, I think, can I think I will introduce about you to your audience. All right. Okay. So Professor Graham Gus Jonathan, PE, PhD and GPA and 5A Aust is actually Director Center for Energy Technology at the moment. So Professor Graham, Professor Nathan, can I thank you? Yeah, Professor Nathan actually graduated from Mechanical Engineering University of Adelaide, and then we continue with the PhD, I think, yeah. And he very intense in the research, especially on the areas energy system, as well as fluidization. It's quite a lot. I think for the experiment in professional engineer, and then for example here, he is professor and director Center for Technical School of Mechanical Engineering, University Adelaide, Australia. From 2007 up to present. And then Professor Nathan as well has a lot of awards. For example, he also have some supervision of the year nominated in 2002 up to 2003. And then as well as he from the Australian mathematics competition. It's quite a lot. And then now we are, I think, waiting very much for your presentation on the heat and mass transport in turbulent particulate flows under condition of relevance to industrial reactors. As well, I think here we are very interested in your topic because it is very important, I think, in the next hour energy. So please, your time, Professor Nathan, that's about 30 minutes, I think. So enjoy your time. And then please, that's for you.
Thank you very much, Professor Samsol. And selamat pagi, and thank you to the organisers. It's great to be able to participate in such a great conference in this important area of thermal fluids. And so the talk I'm going to talk on really covers the thermal aspects as well as some of the fluid dynamics, talking about, and I see I left off an N here, sorry, particle-laden flows, but under conditions of relevance to industrial reactors. These are the reactors used to produce things like cement, alumina, etc., where particles are transported in suspension, and they're heated at high heating rates, but also a number of other technologies as well. I would like to acknowledge the contributors. We have quite a large team here at the University of Adelaide, and these contributors also from our team have contributed to this work. And also I would like to mention that we're certainly very interested in exploring opportunities to collaborate and would welcome further opportunities to discuss that. So this topic is really driven by the need to manage or mitigate CO2 to decarbonise the industrial sector, and particularly the heavy industrial sector, which are the energy-intensive processes. So the figure in this top left is one produced by the International Energy Agency, Cedric Philibert, looking at the global contributors to CO2 emissions in the next 50-odd years. The purple sector is the electricity sector, which is expected to decarbonise first because obviously the introduction of things like renewable wind and solar PV. Then the orange line is the transportation sector, which is also, we have a pathway to understand how that will decarbonise, whereas the blue line is the industrial sector, and you'll see that this is expected to decarbonise most slowly, so that in 50 years' time it would become the dominant source of global CO2 emissions, because it's more challenging to decarbonise in the other sectors. And if you look at currently this 32% of the industrial sector, or the industrial sector contributes 32% to current global CO2 emissions, which is this sector here. And of that, about 3/4 of the demand is for heat. So this is why thermal fluids is important. And of that, about half of it is high temperature heat, which is shown in these two sectors here. In this particular assessment, Cedric Philibert judged high temperatures being 400, but in fact most of the industrial temperature, the industrial processes run at temperatures above 800, things like cement and alumina. And in these cases, these are where there is no real commercially available solutions yet to do these with low carbon energy. So this is an example of some of the types of processes which occur The figure on the photograph on the left is a preheater and precalciner tower in cement manufacturing. You see particles are transported blown up in suspension up this tower, and they move through a series of cyclones where heat is transferred, etc., and then into a reactor, and something like a calcination reactor, where currently the heat is provided by combustion, by burning fuels in these densely laden flows, suspensions of particles. Alumina is a similar process, also heated in powders. These are particles of the order of 100 micron, the 10th of a millimeter or so, a bit larger. And also, importantly, there's quite a high mass or volume loading. Actually, the mass loading is up to about 1 to 1. The volumetric loading is about 1 in 1,000. That's actually a volumetric loading there. I apologise for that. I just noticed that slight error. So the reason why these processes are challenging in the current global context is because most of these processes, for example, iron and steel, cement, lime and alumina, all of these processes, these are some of the temperatures that they operate at, and there are a number of emerging low carbon technologies or low CO2 technologies under development, but most of these are at pilot or large scale development. There is no real commercially viable demonstrated ways of still maintaining economically viable production whilst achieving carbon zero net production. So this is a substantial research challenge which will be expected to continue till 2050, and this is a challenge which our centre is particularly focused on, and we welcome opportunities to collaborate. So one of the emerging pathways for heat, some of these is electrification, some of them is also hydrogen, and some of them is concentrating solar thermal energy. And this, I mentioned this approach because some of the emerging technologies for solar thermal, potentially the target is to get to high temperatures of 800 or 1,000 degrees or more for those industrial processes, but also for more efficient electricity generation. So a number of groups around the world are working on ways to achieve high temperatures. And an example of one of the, there's several ways, but the leading methods all involve the heating of particles. So this is another application why we need to study high temperature and heat transfer in particle-laden flows. In this case, what has happened is a stream of particles are taken to the top of a tower, and then the particles fall into a curtain, a thin sheet of particles falling down, which are then irradiated by the radiation from heliostats to generate high temperatures. So the commercial technology is shown in this photograph on the left, which commercially typically drives a steam turbine and only achieves temperatures of about 580 degrees Celsius. These are the things that use things like the molten salt, which would be in this tank here. But the technologies of the future are likely to use things like particles, and there's a lot of researchers around the world, including ourselves, who are looking at these methods of heating particles with radiation. So all of these methods, be they the industrial processes, they need to be heated to high temperatures, and radiation is one of the methods, but also the study of particles heated by radiation is also relevant to some of these emerging technologies, such as concentrating solar thermal. There are a number of these technologies under development around the world. This is the falling particle curtain I just mentioned here. This would heat particles falling through this curtain. They go into a hot storage tank, through a heat exchanger to a cold storage tank where they're recycled. This is a program being led by Sandia National Laboratory, and the Australian Government Lab, ourselves and a number of others are all working on this program in an international collaboration. But there's another one being developed by the German research laboratory DLR. We're also working with them on this technology. There's a number of groups working on fluidized bed reactors, and in Adelaide we're also working on a different type of technology called a vortex receiver that I won't go into in too much detail. Just to say that there are a number of these applications being developed in parallel, which around the world means that there's de-risking the pathway that one of them or more of them will probably be successful in different applications, but all need the study and understanding of how to heat particles in suspension to high temperatures by radiation. So what does it look like? This is a pilot scale facility. This is the one in Sandia in Albuquerque, and you see these are the particles. Zooming in, the heliostats focus their radiation into this little box here, which zoomed up. This is the curtain, and you see the curtain falling down. Instantaneously, you see there's evidence of complex aerodynamics in this curtain, and these are the kind of things we need to study if we want to optimize the heat transfer in these processes. Clearly, we'd like to be able to heat the particles and minimize the irradiation losses and minimize the heat transfer to the surrounding air in this case. In other cases, they're different. The vortex receiver we're working on in Adelaide, I'm not going to go into too much detail other than saying this is a cyclonic type device where particles are carried in suspension and also heated by radiation. So we're doing quite a bit of work on this, including measuring velocity, etc. I'm not going to go into it in detail other than to say it's another reason why we need to understand heat transfer of particle flows in suspension. So I'd like to return to the fundamental program we're looking at to try and understand these heat and mass transport processes in particles in suspension. And we're studying a jet coming out of a long pipe of particles which are in suspension. So the particles are transported by the pipe and then they emerge into a surrounding co-flow of air. And you can see this is an instantaneous snapshot, and you can see the particles are not uniformly distributed, but they form preferentially into these local regions of high concentration and low concentration. And these are often called aerodynamically as clusters. They don't mean they're not necessarily sticking together as agglomerates, but aerodynamically they're closer together. And this has been a term that's been coined, particularly by Professor Eaton in Stanford, and following that, the term clusters has become adopted. So if they're heated by radiation, you can see that the radiation would be attenuated through this because there's a lot of particles in these media. There's high volumetric loadings, and the aerodynamics is a two-way coupled, means the momentum of the particles is big enough to influence the fluid, but also the fluid influences the particle trajectories. And then there's a lot of interaction between the radiation, scattering, and then the particles are heated, and then they transfer the heat by convection to the fluid. So we'd like to understand these complex dynamics, and I'm just going to tell you a little bit about some of the work we're doing to start to better understand these details. So at Adelaide, we've been setting up quite a unique and complicated system for progressively advancing the understanding of the measurement of these different components in this multidimensional system. The system comprises a wind tunnel, a low velocity wind tunnel, with a stream of particles coming through a jet, which are transported down the middle of the jet. There's a co-flow around the outside, and also a coannular flow. The coannular flow allows a different type of seeding, matching the velocity of the co-flow, but to allow you to seed particles or some other gas into that medium without influencing the whole system. So then, through this, we use a number of optical methods. We use the green beam, is actually a combination of several different laser systems, which are imaged by cameras. These are for measuring velocities and temperatures, etc. And this orange beam is a high flux heating laser, a high powered heating laser that heats by radiation in a small zone to very high fluxes, commensurate with even higher than in those solar concentrators, the order of 30,000 suns or more, 30,000 megawatts per square meter. So in this system, what we're setting up for measuring the heat and mass transport processes in a particle-laden stream subjected to high flux radiation, and it's also relevant to many other cases. So briefly, this system with the green laser, the 532 YAG, is for measuring velocity. Then there's a system for measuring the temperature of the particles. So special particles are seeded in which give a phosphorescent signal that depends on temperature. and by exciting that at a certain wavelength, which is the frequency tripled wavelength, then we get the measurement of the particle temperature, and another system can be used to excite different wavelengths for measuring the gas phase temperature, also when seeding a certain fluid. This is for a fluorescence method of the gas phase temperature, and I'll show you a bit about those. I won't go into too much detail of the methods, but before going into the whole system, I would like to show a few of the insights we've obtained firstly in the isothermal case. So this is a non-heated system, simply by looking at the distribution of particles in a particle-laden flow. This is non-heated, it's just looking at particle distributions in this case. And the dimensionless parameter used to characterize the aerodynamic response of particles in a flow is called the Stokes number. Stokes number is a dimensionless ratio of the response time of a particle to an aerodynamic eddy, and the fluid time is the time scale of the eddy. So a simple way to think about it is a small tornado. In Australia, we call them the dust devils or the whirly-whirlies, a little cyclone of air picking up desert sand in the hot sun. And you can imagine then the dust particles are small enough to follow the eddy, so they've got a Stokes number that's less than 1 because the particles can respond to that eddy. But if you were to throw a brick through that eddy, well then this would then become a high Stokes number. The brick would go straight through the cyclone; it wouldn't see it. So that's a particle that doesn't respond to an eddy. So you can see here that for small Stokes numbers, the particles are preferentially distributed on the outside, and then as you go order 1, you see you get quite different distributions. And for the large Stokes numbers of order 10 or bigger, the particles are preferentially concentrated on the axis. So you can see just from this image, this is for monodispersed particles, but the size of the particles influences both the distribution of the particles and the total spread. So we'd expect perhaps the smaller particles, the low Stokes number, to spread more, and the bigger ones to spread less, and we see that, but you also see very big differences in the way in which they're distributed in this system. So we've been looking at those, but in addition to that, if you take an instantaneous image, you see that you get very different evidence of these clustering effects depending on the size of the particles. When the particles become very small, as the Stokes number is very much less than 1, approaches 0, then you see they become a flow tracer and you don't really see much evidence of clustering. On the other hand, as the Stokes number is order of 0.3 or less, we get strong effects of clustering. And as the Stokes number gets big enough again, 10 or more, then again we don't see much evidence of clustering. So you see the size of the particle influences not only the total distributions, but the instantaneous. And you can imagine that the heat transfer and the mass transfer inside these clusters will be very different from that outside. So we need to understand them if we want to be able to optimize and design the future technologies which will be carbon neutral. So just perhaps a nice image to show these instantaneously in more detail. You can see these clustering effects are really very clear when you assemble them together. So in terms of the mean distribution, this is a cross-sectional distribution. This is the radial distribution of the mass loading through the exit plane of the jet. And again, you see the small particles are preferentially distributed on the walls, and the big particles are preferentially distributed on the center. This is the mass distribution of particles, it's not velocity. All of these have got a velocity distribution that approaches a fully developed flow. So the velocity hasn't changed, but the mass distribution of particles is very much changed. We've done some analysis on what we think the cause for this is, and we think that the big particles are dominated by Safman's lift, and the small particles are dominated by the turbophoresis. This still needs some more work to fully confirm this, but this is some of the kind of work we've been doing to try and understand the average distributions. In terms of a bit more insight into these clusters, one of the things that we've done is develop automated methods for quantifying what is in a cluster and what these dimensions are. And you can see this is a morphing method. That this is the red lines are an automated method that picks up where the clusters are, just to illustrate that they give good alignment. I'm not going to go through the details, but basically there's a whole series of data processing methods that you put through to select the background, develop masks, and from that you can discriminate, what is in a cluster and what is not in a cluster, and that then allows us to put some numbers on the size of these clusters, which helps us provide some insight. So without going into the details, the key figure I'd like you to look at is this one on the right. This is the distribution, or the probability distribution of the most common width of those clusters. And you see that the width of these clusters is typically around about 20% of the diameter of the pipe. So that means these clusters, so that is just going back to here, for example, that's the width across one of these cluster images is around about 20% of the diameter of the pipe. That's the most probable dimension. So but the length of them is 10 times or so more. So this tells you that these are associated with the large turbulence eddies that are transporting the system. You can see that these clusters span the width of the jet. The spacing between them is also the order of the pipe diameter. So they're generated by the large eddies in the flow, even though they're relatively smaller scale themselves. We've done a whole lot more of this stuff that I'm not going to go into detail, but we can give you more if you're interested. But you can see the key points we found from the isothermal flow is the mean flow itself. Distribution depends on the Stokes number. As you saw, the distribution of particles depends on the size. The clustering depends strongly on their Stokes number. The size implies that they're generated by the large scales of turbulence. I didn't present any data on this because of time, but I can later in the question if you're interested, that we have shown that they're also rope-like in shape rather than being sheets, and they depend on the upstream flow. This means that the time scale for these to propagate is hundreds of pipe diameters, so they're very long-lived structures that depend on the large-scale aerodynamics with long history effects. But a lot more needs to be done to understand them properly. I'm just going to give you a snapshot of some of the insights that can be obtained when we then add heating. So this is that red line I showed in the earlier slide. This is the high flux heating laser. This produces 3 kilowatts of continuous radiation at about 900 nanometers into a small waste of about 10 millimeters across. Now, 38 megawatts is hard to put a reference on until you do something like this. This is what happens with the laser on for about half a second on a brick, and it gives you an idea of how much energy is in that beam. So this is that laser passing through a system of a jet, and then we've incorporated into this some of the optical methods for measuring the temperature of both the gas phase and the particle phase in situ. I'm not going to go into the details of these methods other than to say that what is done is the thermophosphorescence method. The particles are coated with a phosphorescent material, coated or solid material, and then the intensity at 2 different wavelengths. So they're excited at a wavelength 355, which excites this phosphor for this case, and then we collect 2 images with different wavelengths. One is at 440 nanometers and one is at about 390, and the ratio of these 2 wavelengths gives a measure of temperature. So what does that mean? You can see here that the signal depends on the temperature. As the temperature changes, the spectral response changes, and the ratio of these can be calibrated to give a temperature dependence. So to give an example of what that means, all this in line column A and column B, this is the same particle imaged through 2 cameras with those different filters. One is imaged at the 440 nanometers roughly, and one is about 390, and the ratio of those is what's in column C. So you can see as the laser intensity goes up, the particle temperature measured particle temperature goes up, but this is determined from the ratio of two images of the particle. And then a similar method is done for measuring the gas phase flow, and in this case it's also a two-wavelength method, but in this case it's two-wavelength fluorescence, and the gas phase of nitrogen is bubbled through toluene, and this therefore carries a weak concentration of toluene into the nitrogen, and then again that is excited, in this case by 266 nanometers, and the ratio of those two wavelengths gives the temperature of the particle phase. So again, two filters, and this is again, these are the signals of the two different wavelengths, and the ratio is this line here, which responds proportionally to temperature. So I'm not going to go into the details, other than to show you three images of the insights that can be obtained, and we're in the process. This one here hasn't yet been published, but it will be soon. So what we're looking at here, at the top of these images, is the exit of the pipe. So pipe transporting the particles, in this case with the toluene seeded nitrogen flow. So it's a flow, it's a jet of particles which is not reacting, but then the carrier gas is nitrogen with a small amount of toluene introduced coming down here. Then the heated laser comes through between these two lines here, in the line with this red beam here. This is dimensions, so this is in diameters. It's about 1 diameter width is where this laser is heated, and in this case, this is the signal from one wavelength and the other wavelength of the toluene fluorescence, and this line is the scattered image from the green wavelength, which shows where the particles are. So this first case has got no particles in the system, and so you can see, although the laser is on, we don't measure any temperature rise in the gas because we're only heating the particles. Sorry, there's no particles to absorb the energy. On the other hand, in this case, there's no heating laser, but there are particles present, and once again, we don't see any temperature rise in the jet of fluid. So now in this third case, the laser is turned on and the particles are present. So you can see the ratio of this red and this blue color is what gives temperature. And if we zoom in on this box, you can see that there are zones of high temperature gas which are associated with where the clusters of particles are found. So we see that there's even though the heating occurs upstream, initially it takes time for the particles to transfer the heat to the gas phase. So it's convection limited heat transfer, and then this convection is then leading to locally very high temperatures of gas around the particles, but other zones which are very, very low heat transfer. So this tells us that the clustering is having a big impact on the heat transfer between the zones where particles are present and are not present due to the effects of clustering. So we haven't yet begun to fully analyze this data. This is still in progress, but we can still draw some key conclusions. Key conclusions that we find is that the particles in these two-phase flows are dominated instantaneously by these aerodynamically generated clusters, as they're termed. This is not, the particles don't necessarily stick together, they're just closely located. And these have got a shape which is rope-like in shape in these clusters. So they're highly non-uniform instantaneous distributions of the number density. Inside the cluster is much more distributed, much more concentrated particles than outside, and these have very long history effects. So the clusters are generated hundreds of pipe diameters upstream, and they propagate throughout the flow. So these are generated by the large-scale eddies in the fluid, even though the scale of the clusters is much smaller than the diameter of the large eddies themselves. So this tells us the development time due to the much greater inertia of the particles. This is why there's these very long history effects. But this also means if you're going to model these, you need much greater computational intensity, which is the computational challenge, so we need to have better understanding to be able to develop simplified models that can be applied to engineering design tools. There's still a lot of work needed to be done here. The Stokes number, as we've referred to, influences both the mean and instantaneous flows. And in the mean flow, we see that, for example, the small particles are preferentially distributed close to the wall of the pipe and the big particles on the axis. But also the clusters occur most strongly in the certain Stokes number range of about an order of magnitude, maybe a bit more. And these clustering effects also have a big impact on the heat transport, that the fluid within the clusters is heated more, and the mixing between the clusters is quite significantly inhibited. And so this needs to be studied and optimized because it'll have a big impact on performance of these reactors, which need to be optimized if we want to achieve cost-effective technology in the future, low-carbon technology that's needed for our low-carbon future. There are a lot of ongoing challenges as well, which I won't go into now, but if people are interested in collaborating, we want to better understand these mechanisms, we want to improve our methods of quantifying them, and also we need to continue to develop the methods, both optical and numerical, to be able to understand them, and also to be able to understand particularly into these more heavily laden regimes. So I hope that's given some insights, and thank you for listening, and I'll be happy to take any questions that we have time for.
Thank you very much, Professor Nathan. That's another very, very good presentation, as well as a very important information in his presentation. I think in connection with the low carbon CO2, I think from Paris Agreement, at the moment, each country has let's say, a commitment to reduce the CO2. So this is very important information for to be included or to be considered in how to reduce it. That's great. Okay, give applause to Professor Nathan then. Okay, now I think we have come to the question and answer time, and we have about 15 minutes in here in the question and answer. So I think first of all, here we have a question first from for Professor Sutrisno. I think, would you please, your Professor Sutrisno? First, the question is, will the presentation slides be shared with participants? That's great, I think. And secondly, that is from Canada, Martha, the aircraft cruising in the air, does the water tunnel test will produce equal results as the wind tunnel? This is an enlightenment, please. Thank you. All right, that is two questions for Professor Sutrisno. And then for Professor Nathan, you have right, this is from Akmal Irfan Majid. Dear Gus, thanks for your impressive presentation. We hope to establish a future cooperation with UGM to analyze the particles in modeling side. Did you also consider to conduct the discrete element model, DEM, simulation, which can be right, it can be right, can be coupled with CFD thing. Is the single particle model for or just a partial approximation required to explain the phenomena? All right, that is one question, but I think it's quite a lot to be answered. All right, so I think first of all, I think for the time is for you, Professor Sutrisno, to answer the two questions, please. Yes, Professor Sutrisno, that's your time. Okay. Hello, Professor Sutrisno.
Okay. Can you hear me?
Yes, please. Yes, sure.
Could you give me the first question, please?
Okay. All right. I will. I'll give you the first question. Will the presentation slide be shared with participants? Of course, I don't know. It's up to you.
I think
Can be shared.
Yeah, but I have shared to the organizer. It's up to the organizer whether gonna
All
be.
right. Thank you very much.
Yeah.
Great answer.
Yeah.
Okay. So how about the second one?
The second one is
Okay.
we do measurement in the water tunnel. We have proof that the accuracy is very, very high. This one is done by America and France. And my water tunnel is developed based on those design. And we prove also several experiments that match very well with the real CL, CD, and CM. So we believe the accuracy is very high. And the problem is, this one, I believe Singapore has, Australia has for the water tunnel because the accuracy is very high. But in America, a water tunnel is not famous because electronic in America is very complicated. Therefore, for them, measuring using water tunnel is not fun. So basically, they believe they like to measure it in the water tunnel with high size, with a big size, 4-meter diameter and something like that. But for the aerodynamic in Indonesia, Singapore is not that big. So that's why water tunnel is good for a small country like Indonesia. Okay.
All right. Okay. Yeah, I think is already answered the question. So maybe some people wondering because the aircraft is flying in the air and then you studied in the water something like that. So is this what is the is this? Yeah, that's right. Okay. So I think this, you already answered the question. So the next, I think we go to Professor Nathan. So please, your time to answer the question.
Thank you. Firstly, of course, I'm very happy to share the PowerPoint slides, and I'll make them available to the organisers shortly. Secondly, the question I think was around DEM modelling. In fact, we are exploring both together and in collaboration with a number of collaborators the different options for modelling these phenomenon. And certainly DEM is one of the approaches that does make sense, particularly in the very densely laden environments such as the outlet from the falling particle curtain system. Nevertheless, this needs to be done in collaboration with experiments because there are phenomena that are not necessarily accounted for in present approaches with either DEM or CFD. What we find in the curtain, for example, is the DEM is good in the initial stages, but then as the aerodynamics become important and start to generate the clustering phenomenon further downstream, this is not so well incorporated in DEM, On the other hand, CFD, also there are a number of approaches need to be undertaken together. Of course, things like, there is work being done already with direct numerical simulation. However, these are limited to relatively low volume loadings and also to modest size computational domains. We think that it's difficult to incorporate the full the long history effects of these clusters because of the very long computational times required in the inertia of these clusters. So we think there is also going to be a need for developing simplified models that combine detailed experiments with the validation and insights together. So this is a very challenging regime that will take a lot of collaboration of different modeling approaches and different experiments working together to start to develop the new improved models, especially if they're going to be looked at industrial scale systems. We obviously need to have simplified models in those cases, but they do need to be able to reliably account for these effects, at least over limited ranges of conditions. So we are keen to work with different collaborators who want to work with different tools collectively. We are very happy to make all of our data publicly available and to share them with people who want to work with modeling techniques. We are also working with the falling particle curtain. I didn't present any data on that, but we're developing a very systematic condition. All of our experiments are carefully designed to have very well-defined inflow and boundary conditions to assist with the development and validation of models. So if there are people in this meeting who would like to work together in that, we would welcome those opportunities.
Okay, thank you very much, Professor Nathan. I think that's certainly answered the question. And then there's another person that is Mr. Rafi Fajar, who is interested with your presentation, Professor Nathan. He asks about, will heating laser technology have room to develop more in the future? That is the question for Professor Nathan, please.
This is a very good question. This particular laser that we have is model number 001. So it was developed by one of my partners at the University of Adelaide, Professor Ziad Al-Wahabi, and he worked with a laser company for this to be the first of its type. But of course, this field is developing very rapidly, and also high flux and high powered lasers are being used for things like welding and all kinds of new systems. So if you'd like to work on the laser itself, I can put you in touch with Professor Al-Wahabi, who's a specialist in the laser development.
All right. Great. Okay. Great. I think it's already answered all the questions for you both, Professor Sutrisno and Professor Nathan. So I think it's quite time to finish this presentation after as well as the question and answer section. Okay, I think it's great applause for you both, Professor Nathan and Professor Sutrisno. All right.
Thank you.
Okay, I will give the time again for the committee. Please, thank you very much. Thank you very much.
Right.
Okay, bye-bye.
Thank you very much to Professor Samsul Kamal as the moderator, and of course to the keynote speakers, Professor Sutrisno and Professor Gus Nathan. It was a very interesting presentation, and very interesting topics were brought to the table, and I myself, as well as a spectator, feel so honored and interested as well to pay attention and to sort of put a lot more studying efforts towards those particular topics. Next, we are going to move swiftly onto the renewable energy and energy harvesting paper presentation. And for this particular session, the moderator would be Professor Tri Agung Rohmat. I'm sorry, is this correct? No? All right, so we'll be, sorry? Okay, sorry. I've just been informed by the committee, apologies. So the next moderator would be from Mr. Triagung Rohmat. And to Mr. Triagung Rohmat, if you're already there, the time and the platform is yours. Thank you very much. Okay, Mr. Triagung, can you hear my voice?
Yes, yes, yes.
Okay, please continue, sir. The time is yours. Thank you.
Okay. I have to check if all participants is ready. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. We enter section 1 of the Thermofluid 11 conference. I'd like to welcome you all on behalf of the Thermofluid Committee. And we can see from the program that we have 5 presentations in this section. I'd like to remind participants that they have a maximum of 8 minutes for their presentation, with 4 minutes allocated for question at the end. I have to check if Mr. Sirajuddin and other researcher are ready for this section. Mr. Sirajuddin, do you hear my voice? Mas Fakhri, do you hear my voice?
I can hear you loud and clear, sir. It's clear.
It's clear. Mr. Sirajuddin, are you ready for your presentation? I'm sorry that the presentation time is have to get earlier than the agenda. Mr. Sirajuddin, Mr. Fajar, Mr. Soekarno. Do you hear my voice?
I can hear your voice, sir. I don't think there's a problem with the connection.
Okay.
Perhaps if the presenter isn't here yet, maybe I'll try and ask help from the organizers to contact them, etc. And maybe you could keep calling or keep doing the roll call until there's a presenter that's here.
Okay.
If you don't mind, sir. Okay. So please stand by, and I will try and contact the organizers and the team here.
Okay.
Sorry, Mr. Triagung, can you hear my voice?
Yes.
Perhaps if the presenters that are up front on the order aren't here yet, perhaps you could keep moving on to the list until perhaps there's a presenter that's already present and here.
So for I proceed for the next speaker.
Yes, I guess you can do that, sir, and then I'll try to coordinate with the committee here to sort of shake up the order again. Yep.
Okay. I'm sorry, Mr. Ibnu Royhan.
Yes, I'm here.
Okay. Are you ready for your presentation?
Yes. Okay. I will share screen.
Okay. It's my pleasure to introduce our first presenter for this section, the group of researcher, Mr. Ibnu Royhan, Mr. Kinan Chandra Putra, Mr. Eko Astiawan, and Mr. Raldi Kostur, who will speak on usage of solar box care. Time is yours, Mr. Ibnu Royhan.
Okay, thank you. Do you see my slide in your computer?
Yes.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Let me introduce myself. My name is Ibnu Royhan. I will present the result of our research entitled Installing and Testing the Grasshopper Portable Incubator powered using the solar box BCare for remote area without electricity. Me, Kinan, and Mr. Raldi from Heat Transfer Laboratory Engineering, Universitas Indonesia, and Mr. Eko Setiawan from Electrical Engineering and Tropical Renewable Energy Center. Okay, this is the background. Indonesia ranks fifth in the case of premature babies in the world. Grasshopper Portable Incubator as one solution to help premature babies. Grasshopper Portable Incubator has been a community engagement since 2012 until now. The problem is that although the electrification ratio in Indonesia has reached 95%, in some places it is still below 70% and frequent blackouts. One solution is to use electricity from the sun because Indonesia has high potential. This is the portable Grasshopper incubator. In the principle, the Grasshopper incubator uses 2 units, 25-watt incandescent bulbs, which natural convection will make the baby's cabin temperature rise. The temperature is maintained around 33 until 35 degrees Celsius according to the needs of the baby. This is the BCare solar box. Actually, this product has been used well in the supplying electrical energy, and it's in the emergency for victims of the earthquake and tsunami disaster in Palu and Donggala as temporary electricity supplies at the time. The BCare solar box includes 2 units of 20-watt peak solar panel and 2 units 12 volts dry batteries. The purpose of this study includes feasibility test of solar BCare for the use of incubators in actual condition. Besides that, we want to know the charging and discharging process during use in actual condition. From these two things, it can be seen whether solar BCare is appropriate to be used as independent power supply for the incubator in 1 until 1.5 months of use. This is the methodology. In order for long battery life, in accordance with the previous studies, that the battery voltage limit should only be 18% of the total capacity. In this case, the lower limit of the battery capacity will be 11 volts. Solar panel, we use 2 types, 40 watt peak and 100 watt peak as performance comparison. The first test to find out how long the duration of charging without load, starting from the lower limit 11 volts to the maximum capacity that can be stored by the battery. The second test is charging and discharging simultaneous. The load given as an incubator when used normally. The incubator works for several days non-stop to see the charging and discharging condition can be obtained during the day and full discharging at night. This is an experimental setup. Testing into place rooftop location for taking solar voltage sensor. Rooftop location for the taking solar voltage sensor data solar beaker, and location in the room for collecting temperature data in the incubator cabin. Retrieval data using two solar panel variants of 40 and 100 watt peak and test full for one full day. The inverter is used to convert electricity from 12 volt DC to 220 volt AC for needs of the incubator. This is the experimental setup real. So we can see the solar box in the rooftop, then the incubator in the non-AC room. This is the result of charging without load. This is a charging chart for 40 watt peak solar panels without load. The red line is the measure voltage of the battery, starting from 11.5 volts to 14 volts. The duration required to fill up takes more than 5 days non-stop, with an average increase of 0.1 volt per hour, and the most optimal is 0.25 volt per hour. For 100 watt peak solar panel without load, it only takes about 26 hours to charge from 11.5 volt to 14.5 volt. Optimal charging reach 0.38 volt per hour. This is the graph of 40 watt peak solar panel usage with the loading. In the graph, the temperature can be maintained according to the controller, which is around 33 until 35 degrees Celsius, with an average ambient temperature around temperature ambient around 30.5 degrees Celsius. But if you see from the battery voltage, seen in the one full day continues to decline even during the day. Nothing show the battery voltage increases during the day. This proves that no charging process occurred. It can be concluded that the 40 watt peak solar panel cannot recharge the battery and cannot be used for incubator. This is of the use 100 watt peak solar panel with loading. The temperature in the cabin locks can be maintained according to the controller, that is 33 until 35 degrees Celsius, with an average ambient temperature around 30.8 degrees Celsius. Compared to 40 watt peak solar panels, 100 watt peak solar panels can recharge battery during the daytime, but the charging process doesn't reach the maximum value of the battery voltage during initial use 14 volts. This makes the use 100 watt peak solar panels not yet safe for growth of incubator. This can be seen from the rate of the voltage increase, just 0.22 volt per hour, while the rate of the voltage drop is 0.28 volt per hour. This is a conclusion. The conclusion is that during sunny weather, 40 watt peak cannot charge the battery, so it is not suitable for incubator use. But for the 100 watt peak panel problem, it can be used even though it is still not safe because the rate of increased voltage is lower than the rate of drop voltage. However, the solar box beaker can be used as a source of electricity for the growth of incubator if it is retrofitting and replacing large capacities of the components currently on. Thank you for the time. we can to back to moderator.
Okay, thank you, Mr. Ibnu Royhan. I hope the other participants ask some question or comment on some of the points of the speaker made. Please, the participant, you can ask the Mr. Ibnu Royhan. Okay, as nobody seems to be ready to ask a question, I'll use this opportunity to ask the speaker.
This is any question from the Q&A column?
Oh, okay,
from
okay.
Frahi Fajar.
Okay.
Oh, no. I'm sorry. This is the question from before presentation.
Yes, it was a question from the previous presentation. So
Okay.
I guess so far there hasn't been any question
Okay.
yet.
Thank
So
you.
back to you, Mr. Triagung.
Okay. I think it sounds promising, utilization of the Grasshopper incubator coupled with solar box care in remote areas. Do you have plan to commercialize this copper product in the future?
Okay. Actually, this product not commercial, but this is product especially to what we call community engagement. Just it because we want to help the more people, especially privileged, unprivileged community. So the baby parents who cannot land or landing to incubator in hospital, we can help the family and the babies. So because the specification, design, and others, we special to community engagement and especially for to home incubator in Indonesia, especially about iklim. This is, thank you.
Okay, thank you. This next presentation, I'd like to express our appreciation for your interesting presentation. Okay, we'd like to move on the next speaker. Thank you, Mr. Ibnu Royhan.
Okay, thank you.
I'll call again Mr. Sirajuddin.
Okay, yeah. Yes.
Are you ready?
Ready, inshallah.
Okay. The next presenter is the group of research, Mr. Sirajuddin, Mr. Fajar, and Mr. Sukarno, that they will speak on Bangki Turbine. Time is yours, Mr. Sirajuddin.
Okay, can you see my PPT?
Okay.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Please slideshow your PPT.
Yes.
Please make your PPT as slideshow. It's very small.
Very small. Maximize.
Oh no, slideshow.
This is my. Can you see my slideshow? My slide now. Here. I already present my slideshow.
I don't see your slideshow.
Oh. Slideshow.
Boleh saya benerin. Bukan itu, Pak.
Sorry, Mr. Sirajuddin, can you put it to full screen? Can you full screen your presentation?
Full
And
screen.
so that we could, yeah, so that we could see it clearly. It's on the bottom right corner, if I'm not mistaken, bottom right corner of your
Di bawah.
screen.
Nah itu Pak. Bentar.
You can put it into the presentation mode so that everything becomes full screen.
Ini Pak.
You can click F5.
Yes. Can you see my slideshow?
Okay, okay.
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 Okay. Okay, thank you very much. My respected ladies and gentlemen, my name is Sirajuddin from Mechanical Engineering, Universitas Negeri Jakarta. I want to present my research about investigation of reduction of Banki turbine shaft diameter to increase power. Background, in the turbine Banki turbine, the flow of water enters through the nozzle to the first and then to the second stage of bleed. The water flow passage in the second stage often strike the shaft, so reducing the power generated by the turbine. This is my research before about the Banki turbine. Examine the effect of Banki turbine bleed profile on strength of the material and water trajectory in the runner, and then investigated the geometry of rectangular diffuser on CFD based Banki turbine, and then investigated the variation of nozzle Banki turbine. Investigated variation the angle of lower guide plate for the internal transit, and then modified the shape of blades in Banki water turbine to increase power. Investigated variation nozzle curve of water into runner Banki turbine using CFD software. Then research the effect of variation and elbow type drop tube shape on the drag force value with CFD software. So the aim of my research was to increase turbine power by reducing the diameter of the turbine runner shaft, so it was not struck by water flow, and the drag force approach was used to predict the power occurred in the surface of blade. This is the parts of the Banki turbine. Number one, diffuser, guide plate, then nozzle, and then for this runner, this is runner, and this is blade. This is blade stage 1, and this is blade stage 2. Then this is a runner shaft, and 5 the drop tube, number 5 drop tube. This is the cross section of the Banki turbine. The method, firstly we made the 2D geometry created in AutoCAD, and then 3D in SolidWorks, and then process in SolidWorks CFD flow simulation. Where is the discharge? 2 meter cubic per minute, or 0.0333. There is some, and this is mistake. 0.0333 meter cubic per second. And they use each variant of runner shaft diameter, respectively 32 millimeter, 30, 20 each, 26, 25, 24, 23, and 22 millimeter. So the initial shaft diameter to 32 millimeter with theoretical power of 1,656 watt. So we will reduce this shaft inside the shaft. So we will see how the increasing of the power. This is turbine parameter, and price speed angle 16 degree, and then bleed angle 30, outer diameter 200, inner diameter 132 millimeter. This is calculation 131.97. We made 132, and then total bleach 18, and then velocity enter the bleach 10.1 inch meter per second. Will runner with 200, runner speed 470 rpm, and then water discharge 2 meter cubic per minute, and then up diameter. In the boundary condition, the operating pressure 1 bar, and then gravitational acceleration 9.81 unit SE, type analysis external, gravitational reference axis X, liquid water, turbulent and laminar, toughness 0.01, adiabatic wall, temperature 20 degree Celsius or 293.2 Kelvin. Turbulent model K epsilon, wind intensity 2%, length 0.03 meter. Rotation, we try to stop a movement for stop movement. We try to analyze in stop a movement. So this is the result of the CFD solid work. This is diameter 32, the original diameter, and this is the pressure 32 millimeter, reduced 2 millimeter, and then 28, 26, and then then 25 and 24. We see that 24 millimeters. We see that the water not strike the sub, and then the water strike the second stage of the bleach into two bleach. This is upper bleach.
Yeah. You've got only 1 minute left.
Yeah. Yes.
You got only 1 minute left.
Okay. And then this is the result of the direct force, and then this is the power. This is original power for 30 millimeter 2.38, and we see that the maximum and 24 millimeter 2.56% increase from the original. So conclusion, based on the experimental result of CFD software above, it was obtained that reducing of sub diameter from 32 millimeter to 24 would increase total power of drag 2.56%, and total power drag from the first to second state of bleach at the initial shape sub diameter 32 millimeters variant SL1 was 1,656 watt, while the highest total power was obtained at the sub of 24 millimeter variant. Okay, thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Sirajuddin, for your presentation. Please, all the participants may ask Mr. Sirajuddin for some points of his speak. Nobody asked Mr. Sirajuddin?
Yes. Yeah, okay, thank you.
No. Please back to the slide of 2 slides before conclusion.
This one?
Yeah, this one.
Yes.
This one.
Okay.
The percent increase for power, I see occurred on SR2, SR3, yeah, why don't you emphasize that SR2, SR3 is also produce the higher power than the original one?
We see that the power drag total is 1,696 for variant SR2. We see in this table.
Okay.
Yeah, so this is this power minus this original divided by original. So this is the 2.38%, like that. And for also for SR6 in 24 diameter, the power drag total from first state to second state is 1,699.8. So this is minus original divided by original. So
Okay.
this is the increasing 2.56%, like that. I think like.
So you don't have to decrease the shaft diameter to 24 millimeters. You just adjust the shaft diameter to 30 millimeters.
Pardon?
It's right?
Yes, yes. So I reduced the diameter from 32 millimeter to 24 millimeter, the shaft. And I can reach the increasing of the power from this reducing of diameter.
Okay, okay. Have you considered the shaft strength if you
Oh yeah,
reduce
I
the
see.
shaft
Yes.
diameter?
Actually, I cannot show in this slide. We already calculate that the shaft not reduced because the torsion integrated with the shaft with the runner body. So the torsion will continue to the runner body and then integrated with the shaft. So the shaft not individually we not independently stand the torsion. So because the shaft integrated with the runner, we already analyzed that this system is not is still ship.
Okay. Okay. The other participants,
Okay, thank you very much.
don't you have any question for Mr. Sirajuddin? If nobody asks, thank you for your Mr. Sirajuddin for your presentation.
Okay, thank you, Mr. Agung.
Okay, we are going to the next speaker. Yeah, Mr. Mujamil Asdiyoga Rahmanta, Mr. Almas Aprilana, who will speak on wind turbine please design.
Okay, Pak.
Are you ready, Mr. Mujamil?
Yes, Pak Tri Agung.
Okay.
My respected former lecture, Pak, when I was study in Gajah Mada.
Okay.
May I share my screen, Pak?
Okay.
Sebentar, ini mana ya? Kok tidak ada? Bentar, Pak. Share screen. Oh, okay. Thank you for the apa namanya ini. Today I would like to present our research with title designing of 500 watt wind turbine blades for manufacturing. We are from PT PLN Persero Indonesia. We from PLN Research Institute conducting research in PT PLN. This is our PLN profile. We are biggest state-owned company in Indonesia, especially in utility industry, and we are our shareholder is 100% of government of Indonesia. And this is only introduction because the regulated price we get subsidy from government with from APBN. Next, the background. The new renewable energy target of 23% in 2025 in the general plan for the supply electricity to PLN. Utilization of wind energy is one of the three main agendas for the reduction emission, namely energy conversion and efficiency, coal conversion, conservation, and the use of the renewable energy. The installed capacity of wind turbines in Indonesia when compared to the total installed wind turbine capacity in the world is still very small. Small-scale wind turbine plant, or PLTB small scale, has proven promising to be utilized in remote location Indonesia. So we focus on the remote location Indonesia. We have a pilot project in Ciheras, elaborated with Pak Ricky Elson in Sukabumi, and the design and material of the blades in accordance with the local workshop capabilities is the key to developing small-scale wind power plants in the region. So we have a challenge for developing the small scale. It is restricted by the capacity of workshop in the regions. The methodology is we have the data, geometry, blade, twist, etc. on 500 watt blade design, horizontal axis wind turbine, studied by PLN Research in 2015 at Chihera Sukabumi, collaborated with Pak Ricky Elson. And then up from the data design, we determine the aerofoil type, especially with NASA standard. And then after we have some of the NASA type, we simulate of the type airfoil type in the Keyblade software to know about the characteristic, especially from the best performance of every type of the airfoil. After that, we analyze by comparative analysis Keyblade simulation results. It is a reduction, so only a little theory. Where from the picture we have lift and drag force, and we try to maximize the coefficient of performance of that with related with the geometry. So the idea is we have some of the geometry type related with NASA standard and CA standard, and then we simulate the type in the Keyblade, so we have some of the result performance from the simulation. After that, we choose the best type. We focus in the coefficient performance and the geometry, which is the performance outlet into the conversing wind energy into the mechanical energy. The higher of coefficient of performance, or CP, the better the blade performance. Based on the best theory, the most optimal blade is capable of.
Mr. Mujamil,
yeah,
you have much time. You have no much time. So I think you are better to proceed to the next slide.
Okay, Pak.
Okay.
So in the simulation setup, we have some of the blade design parameter. We can see in the table 1, and then we test with some of the code with NASA 3412 and so on. And then we have Raynaud and so on of parameter. So we have the simulation. The next in the results, we have some of the characteristic in the every single of NASA or airfoil type with of coefficient of drag and related to the coefficient of lift coefficient, and then the graph of angle of attack and coefficient of lift and so on. This is the results and indication in the picture. And this is the graph between alpha coefficient alpha ratio with coefficient drag ratio. The maximum coefficient of per coefficient drag ratio value for various type of airfoil occurs at an alpha value at around 9 dg with a range from about 35 to 52. And then the maximum coefficient performance value occur when the tip speed ratio value is the range from 4.5 to 5.5 for the various type airfoils. The highest coefficient performance value occurred in the airfoil type NASA 4412, followed by NASA 4415 and NASA 3418, receive the lowest coefficient performance value in the above of simulation. This is our summary of the table of the simulation. We can see about the some of the metric of characteristic like coefficient of performance, maximum tip speed ratio, and then geometry like thickness in millimeter and so on. Based on the summary of the performance, various type of NASA airfoil in the table 2, the optimal airfoil is NASA 4415 with a relatively moderate coefficient lift and coefficient drag ratio, and relatively high coefficient of performance value of around 40%. And the addition, this airfoil is quite tight, 18 millimeter net to tine, so it is hoped that the production process using composite materials will be easier. And the conclusion, horizontal axis wind turbine blade designed with 500 watt power with 3 blade, 1 meter ratios dimension, coefficient of performance 40%, and the ratio of CRR ratio is 0.12 and the ratio value of 6 until 8 meter per second has been simulated with Keyblade software by calculating the type profile of NASA 3412, 3415, 3418, 4412, and 4415. The modeling results show that the NASA 4415 airfoil is the type that has the most optimal performance and the dimension are thick enough so that the manufacturing process is easier. Thank you, Pak.
Mr. Triagung, are you there?
I'm sorry.
Okay.
I forget to mute. I forget to unmute. Okay.
No worries, sir. Please.
There is a question from chat from Mr. Walalawita Wimal Siri. Yeah. Why the design is for very small power rating?
Yes, it is because it is for the small area, like in the remote area. So we have a pilot project in Sukabumi, and then we also plan to make a renewable project in Nusa Tenggara, Pak. So there are a small, very small scale area.
Okay. The other question from Mr. Abdul Muiz.
Yes.
Yeah.
Have you tried CFD like ANSYS as a comparison? Yes, of course. After we have a geometry of by the NASA airfoil type, we simulate the stress analysis from several materials like composite, wood, and so on in the ANSYS. But there is other part of this paper, so I cannot fill the result of ANSYS or stress analysis in details in this presentation or paper. After that, we make manufacturing product by this model and install the model in Sukabumi in West Java.
Okay. And the last question from me, did you consider the wind characteristic in Indonesia? I mean that the wind is not constant at all time. There is differences between day and night, and so on.
From the we actually collect the data by using the apa ya? We have a small when collecting data in Sukabumi or in the remote area to collect the data and then we use the data for design the blade, especially small scale ini Pak, with the when characteristic, so we make the tip TSR, tip speed ratio in a medium scale. So if there are small when speed come to the wine, so the wine will rotate. I think yes, Pak.
Okay. Hope you success for your wind turbine.
Yeah, thank you Pak Tri Agung Rahmat.
Okay, thank you for Mr. Mujamuddin for your presentation. Next, the presenter is the research group of Mr. Osada Jamaji, Mr. Kamal Wimala Soria, Mr. Krismal Boteju, and Mr. Wimal Siri. I apologize if I could not spell the names well. Here, they will speak on alternative solar-powered propelling mechanism. Please, Mr. Osada, for your presentation.
Thank you all. Good morning all. I'm Oshada Gamage from Sri Lanka Institute of Information Technology, Department of Mechanical Engineering. Today I'm presenting a feasibility study on introducing alternative solar-powered propelling system to multi-day fishing boats in Sri Lanka. Moving on to the introduction, fisheries sector is one of the significant sectors in Sri Lanka. According to the Central Bank of Sri Lanka, 1.5 of the nation's GDP is contributed by the inland and marine fishing. Multi-day boats stay in sea for about 30 to 60 days in deep sea. Sri Lanka has almost 4,650 multi-day vessels which supply deep sea tuna to large seafood companies. Prices of the fish in the local market has increased due to the fall price in operating cost. These boats need 7,000 to 15,000 liters of diesel per trip. At the present, cost of diesel for one trip is around 1 million Sri Lankan rupees. These boats comprise a significant roof area which can be used to install solar panels and a charging system. This study involved of the amount of power that can be generated using onboard solar panels. Utilizing this study, hydrocarbon emissions can be reduced from the boats in Sri Lanka, multi-day fishing boats in Sri Lanka. Then moving on to the approach to the solution, we gathered data by visiting several harbors and boat yards. Considering the deck area size, we chose a boat which has a 60 feet length for the study. Then calculating the solar energy, there are two approaches that can be used to determine levels of irradiance at any location. The first approach is to use databases with irradiance information for every location. The second approach is the generation of synthesized data based on the physical attributes and location parameters. The first approach was used here to determine the radiation level available at the Indian Ocean. Horizontal global irradiance level at the Indian Ocean is about 6.5 kilowatt hours per meter square. We use solar GIS databases to get these values. Then moving on to the battery energy, a compact battery pack with a capacity of 10 kilowatt hours was chosen, and with a 80% discharging efficiency. These batteries use MPPT method for charging. The total energy demand is the energy required to propel the boat. The energy demand is a function of propulsion power and ship's cruising duration. For our case, ship was intended to cruise for 1 hour per day on solar power. Then moving on to the mode selection, power needed to overcome the hull resistance at any given speed was calculated from the hull speed software. Propulsion power required by the motor was calculated with a propeller efficiency of 60%. Different types of motors were compared to find the most suitable motor. Considering the weight and the size of the motor, HVH induction type motor was selected. Then, according to the American wire gauge standards, the wire sizes were determined. The recommended wire gauge size is AWG4. The electrical systems inside the boats are to be insulated with polymer nanocomposites. Then motor controller was selected to be compatible with the motor chosen. Then solar panel installation. Solar panels are to be mounted on a roof above the deck area with a height of 7 feet from the deck. Panels with an offset in height in between solar panels to reduce the wind load on the boat. Marine solar panels are selected considering the operational conditions. 30 solar panels are used to cover an area of 50 square meters. The power obtained from the panels is 8.7 kilowatts. Designed alternative propelling system, a chain drive system with 2 chains of 16B standard were used to propel the boat through the same propeller shaft while the engine is disconnected. A disc clutch was used to engage and disengage the motor, engage and disengage the motor. A vibration analysis and a static stress analysis was performed for the chain drive system. There were now Altair HyperWorks software was used to perform these analysis. There were no resonant conditions found under the operating speed. The chain drive structure has a safety factor of 2.5. Then moving on to the vessel stability. Stability of the vessel has high importance in operational point of view. With solar panels on board, the change of stability of the vessel must be determined to account the wind moment acting on the vessel with the solar roof. The wind lever created by the wind moment was determined. The vessel is, the calculated results shows that the vessel is stable in both steady and gust wind conditions at full load. Then a cost analysis was performed. Cost analysis was performed to determine economic feasibility of the project. Payback period was calculated by identifying the cash outflows and cash inflows. Net present value was obtained for utilizing solar power system for 20 years to confirm the economic feasibility of the project. According to the net present value, the economic feasibility of the project was determined. A positive NP value will make the project feasible, but the implementation of the system is up to the operators of the board due to the answer. Yes. Then moving on to the results and discussion. This configuration can produce the propulsion power around 51 kilowatts. There are a number of PV modules, solar modules were around 30. Number of batteries used was 5 battery packs of 10
I'm sorry,
kilowatt
Mr.
each.
Osada. Your time is
Yes.
1 minute left.
Thank you. There are several cash flows identified. Calculated simple payback period was around 8.2 years. The batteries must be replaced in the 10th year of commissioning. Utilization of solar power will save around 6,475 liters of diesel per annum and around 17,094 kilograms of carbon emissions per annum. The return on investment of utilizing this project is around 12.5 per annum. Then concluding the presentation, solar powered alternative propelling system for multi-day fishing boats has been studied. The economic feasibility of the introduced system was evaluated. Project is economically feasible with a payback period of 8.2 years and a positive net present value for 20 years of utilization. Comparing to the existing vessel, solar powered vessel will save around 6,475 liters of diesel per annum and around 17,094 kilogram of carbon emissions per annum. This is a preliminary study where the studies results were obtained with assumptions on some factors such as environmental conditions or cost of the components of solar panels, solar powered system, and ideal working conditions. This concludes our presentation. Thank you.
Okay, thank you, Mr. Osada. Please, the participants, if you have some any question, okay. I will ask you. It's nice idea to use solar energy to propel a multi-disc fishing boat.
Yes.
But I wonder how much space do you need to install the PV modules?
30 modules installed on 50 square meters.
50
The
square
area is
meters.
50 square meters, yes.
It's okay. Also, because it is a fishing boat, did you consider electricity for cold storage?
No, there is another project going on for that, for the cold storage. So we did not connect it with this project.
Okay. Any questions from the participants? Okay, if no more question, I'd like to express our appreciation for Mr. Osada for your interesting presentation. Yeah, thank you, Mr. Osada.
Thank you.
Okay, the last but not least presentation, I will let Mr. Bayu Utomo, Mr. Hima Firdaus, Miss Kutsiatul Lailiyah, Miss Vindasari Ramadhani, and Miss Intan Paramudita present their idea about simulated sunlight for indoor photovoltaic testing. Are you ready, Mr. Bayu Utomo?
Yes, I'm ready now.
Okay.
Can you hear my voice?
Yes.
Oh,
I can
yes.
hear your voice.
Before I start my presentation, I turn off my camera desktop because last session I joined to the room. I cannot see the speakers or participant slides. I think there is a problem with bandwidth. So many meeting webinar today in my office, and I hope if I try to turn off my camera, I can run my presentation smoothly. Is that okay?
Okay, that's no problem.
Okay, I will share my screen. Oh, sorry. Sorry. Oh, I'm sorry. I have problem with my my Zoom. Okay. Okay, I will show. Okay, can you see my slides presentation?
Okay. Yes.
Okay, thank you, Mr. Moderator. Good morning, everyone. Please introduce myself. My name is Bayu Tomo, and today I would like to deliver of our latest work regarding the performance of single large simulated sunlight for indoor photovoltaic testing. I'm going to divide my presentation into 4 sections: background, methodology, result and discussion, and then conclusion. Let's first consider for our background. First, as we know, there is a massive attention for application or development of renewable energy due to the escalating of CO2 emission and greenhouse gas emission. And one of the renewable technology that has a huge attention is PV or photovoltaic. It reached the growth annually. This make the PV technology from this. It is clear that there is a need for the testing method or development of testing method The purpose of the testing method is mainly to determine the performance of the PV module in response to the solar radiation incidency and other environmental effects. Due to of the uniformity and the variation of environmental condition and the degree of repeatability of the test result, when the test is performed in the outdoor, there is a huge attention of developing the simulated sunlight or solar simulator for PV testing method. The solar simulator or simulated sunlight is defined as the device that can provide sunlight effect with a spectral and optical composition similar to the natural sunlight intensity generated by the sun. It mainly consists of light, power sources, an optical filter, and the control component. So the aim of the paper is to evaluate the performance, electrical characteristic, spectral wavelength, and non-uniformity of irradiance distribution over the irradiated PV of the single large simulated sunlight. And the determination of the spectral match and the PV measurement performance beyond of the scope of the discussion. So it will contribute to the limitation of the study. It is the simulated sunlight we use in our experimental lab. We use a tungsten halogen lamp with adjustable teeth angle. Moving to the methodology, the performance was carried out according to the British standard 60904-9, a solar simulator performance requirement. According to the standard, the test object should be divided into at least 64 blocks or 400 centimeters square area of a block. In this case, in our current study, we divided our test plane PV module into 99 blocks. So it will give an area of a block is 36 centimeters square, far smaller than the standard requirement. The experimental test was carried out in the climatic room chamber. This was done in order to minimize the penetration, the sun penetration outside the chamber, and then starting test, we set the temperature of chamber in 25 degrees Celsius. As you can see in the schematic of experimental tests, in order to obtain the optimal performance, we divided the test into 4 different distances, and then the tilt angle of the simulated sunlight was set at 2 various tilt angle, 20 and 90 degree. And the PV collector was set at 40 degree relative to the structure of PV module. We use a monocrystalline PV module with 50 watt peak of power. We use a power analyzer and a solar analyzer to measure the electrical characteristic and the non-uniformity or irradiation level. There must be a spectrometer in the chamber for measuring the spectral match or spectral irradiance of sunlight. So sorry for the missing component. Last, we consider the ISO IEC guide 98-3 2008 guide to the expression of the uncertainty in measurement in order to measure how far the characteristic that we obtained. Oops. Okay. Okay. Moving to the result and discussion. As we can see in the electrical characteristic graphs, the current, the power, and the voltage. The current declined steadily and reached a constant value after 10 minutes operation. This similar pattern happened for the power response, in which reached a steady state after jump to the power of 460 watt. This response quite different to the Satat et al., who found that simulators like took 20 up to 30 minutes to perform stable condition. The further of the uncertainty budget of electrical property shows that the...
I'm sorry, Mr. Payutama, your time
Yes.
is 1 minute left.
Okay, the measure rate of voltaic current power has a statistically different to the characteristics stated by the manufacturer. This is due to the small range of the uncertainty value obtained from the calculation. And the spectral of simulator sunlight is similar to the visible light mentioned in the Isen et al. The non-uniformity of irradiancy measurement shows that both method, pretty standard and some within method, is far to meet the standard classification of solar simulated, specified by the solar performance requirement. The following of the figure shows that the simulated light distribution on figure A and B and A and D has a similar pattern and more symmetric than the others. They also have a small black spot area than the others. As you can see, the blue is the black spot of the irradiancy distribution. Lastly, the uncertainty of budget of measuring irradiancy level shows that the distance of 0.3 meter, the tilt angle of 20 degree resulted in best configuration. This happened to the this also happened to the tilt angle of 90 degree. Has a smaller of the standard uncertainty. It means that both configuration is reasonable to perform the PV test under the simulated sunlight. The conclusion are the non-uniformity level of the present simulated sunlight failed to meet the standard classification of solar simulator specified in the British standard. The number of cell zones taken in the methodology was considered as the possible factor to set valid classification due to the consequence of precise mapping in terms of the number of obtained irradiancy level. As we can see in the methodology, we have 99 blocks compared to the 64 blocks required by the standard. The uncertainty value provided the information that the configuration of simulated sunlight with the tilt angle of 20 and 90 could be a reasonable configuration for performing the test at the distance 0.3 meter and over 0.3 meter respectively due to the small dispersion range relative to the uniformity level. This is my last slide, and thank you.
Okay. Thank you, Mr. Payutama, for your presentation. I will let the participants ask
Okay,
you.
I will switch on my camera.
Okay.
Okay.
Are any participants want to ask the speaker? Okay. There are some standards for simulated sunlight, right? And
yes.
You use the British standards. How different between standard for example, ISTEM standard and the British standards?
as we search from literature like journal, is quite similar between the British standard, GIS standard, and the ASTM standard. The different, if not, I forget, in how to measure, how to calculate the non-uniformity level. So we don't have access of the ASTM and GIS standard. So we prefer to buy to get the British standard or IC standard. So as long as we see in the one of literature regarding the CMOTED sunlight, the ISTM, GIS, if I'm not forget, in the IEC, can use together to compare the performance of solar simulator.
Okay. Any question from the other participants? Okay. If there is no questions, yeah, I'd like to express our appreciation for your interesting presentation, Mr. Bayu Tomo. And
yes, thank you for inviting us.
Okay. As closing the session, I would like to thank again for our for 5 speakers in this section, yeah, for their very interesting and stimulating contribution, and the participant for the valuable following discussion. And I return to Mr. MC.
Okay, thank you very much to Mr. Triagung Rohmat as moderator. And of course, thank you as well to all the paper presenters. It was a very interesting presentation from all of you, and also to all the participants for the very interesting questions and discussions. So our first paper presentation session for today has ended, and we are going to have a break for around 55 minutes until 12:30 p.m. Western Indonesian time. So we hope you all enjoy your break, and we will meet again at 12:30 Western Indonesian time. Thank you very much, everyone.
Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology. Over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology. over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditation. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology. Over collaboration and synergy with the governments, industries, and other higher education institutions, we create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology. Over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology. Over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditation. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology. Over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever. Located in Yogyakarta, Indonesia, mechanical engineering was established in 1959 as one of the oldest departments in Faculty of Engineering, Universitas Gadjah Mada. To meet the high demand for industrial competencies, the Industrial Engineering Study Program was founded in 1998, so the name became the Department of Mechanical and Industrial Engineering. In Mechanical and Industrial Engineering, we are committed to constantly developing into a world-class department in academics and research. We carry out education, research, and community service to meet the requirement of the society and the engineering world. Our excellences in academics have been reflected through national and international accreditations. We provide the best environment and support for all the department members. Various sophisticated research has been consistently delivered through excellent support of technology, over collaboration and synergy with the governments, industries, and other higher education institutions. We create outstanding innovations to deal with multidisciplinary challenges in society. To handle obstacles in society and improve their welfare are our focus. So we observe, empathize, and engineer solutions. We design, disrupt, and reimagine the impossible. Engage in lifelong learning to adapt to new challenges. We translate problems into opportunities. We work for and closely with the people. We seek, solve, and share. We optimize everything to be better. Better forever.
Check, check, sound check, sound check. Okay. Good afternoon, everyone. Welcome back to the 2020 11th International Conference on Thermofluid. So after the break, we hope you've had a refreshing break because, of course, as we all know, there's still plenty of excitement coming ahead in this day's session. So next, without further ado, we're going to move into the fluid dynamics paper presentation session. And I would like you to welcome our moderator for this session, Mr. Willy Prasida. The time is yours.
Okay, thank you for the MC for the time. In this session, in session 2, we will hear 6 presentations about fluid dynamics. Your presentation time is 8 minutes and 4 minutes for Q&A. First presentation will be conducted by Mr. Muad Syawali with the title is the effect of orifice diameter on the water vortex turbine. Please for Mr. Muad Syawali, your time is yours.
Okay, thank you very much, Mr. Willy. Oh, wait, let me share my screen. Okay, am I audible? Can you hear my voice?
Yes,
okay.
sir, loud and clear.
Okay, thank you very much for giving me the time to present. Good afternoon, everyone. My name is Muaz, and I'm from Universitas Indonesia, and I would like to present my paper with title "The Effect of Orifice Diameter on the Water Vortex Turbine by Numerical Methods." So, I am from PICO Hydro Research Group, Department of Mechanical Engineering, Universitas Indonesia. So this is the outline of today's presentations. It's divided into 4 sections. The first one is the background, the purpose and methodology, result discussions, and conclusions. So here's the background. Approximately, there are 7 billion people who live across the world, but unfortunately, 40% of those people don't have proper access to electricity, and most of those people are from developing countries. So yeah, as you can see from the picture, it is the global map, and this is Indonesia. Indonesia is one of the developing countries exist. Okay. According to the report from Ministry of Energy and Material Resources, Indonesia electrification ratio in 2018 has reached to 98%. However, there are some regions, mostly from the eastern part of Indonesia, like Ntb, NTT, Papua, Maluku, and Central Sulawesi, they still don't have proper access to electricity. So Pico Hydro is one of the alternative ways to tackle that issues. So why Pico Hydro vortex turbine? There are 3 reasons here. Scale. In order for us to construct the water power plant, specifically vortex turbine, it doesn't require a large space, and it's also suitable for the small rural area. And also the advantage, because of this small scale of the power plant, it requires less maintenance. And also talking about the efficiency of the water turbines, it ranges from the 75% to 90% the efficiency produced. And also the energy resources. Indonesia has approximately 76 gigawatt water energy potential, and yet we still use it like 4% of those total amounts. So this way is also part of way to maximize the utilizations of energy power in Indonesia. Okay. So for my research, the purpose of this research is to see the effects of orifice diameter towards water vortex turbine performance by varying orifice basin ratio using computational method. So I'm using a CFD methodology for this research. Okay, honestly, there are several stages prior to starting the real simulations, and one of them is setup. So the setup is we actually create a real representations in the site, but we transform it into the simulation part. So that's the functions of setup. So here is the list of my setup for the simulations. Okay, it's the 3D transient domain, and I'm using single phase water fluid. And also the feature I'm using is mass motion features, and also transition shear stress transport. Okay, this is the boundary conditions. So the boundary conditions is divided into four categories. And the water inlet here is the water inlet, and then this is the stripe blade, because I'm going to vary also the angular velocity starting from 150 RPM to 400,000 RPM. Why is that so? Because first thing first, as some of you may from mechanical engineering student, you may recall to turbo machinery equipment course, my turbine is classified to impulse turbine. So in order for us to simulate it, the first, or probably the most input for the angular velocity is usually starting from 100 RPM. So that's why I pick 150 RPM here until the maximum number is 500 RPM. So I'm choosing 400 RPM. And also the orifice basin ratio here are 0.14 to 0.18. It is from research from Mulligan. He is Ireland. He doesn't discuss deeply about the phenomena occurs as a result of this orifice basin ratio. So I am doing the research for him. Okay, this is the second stages, which is mass independency test. It's absolutely to find for the error, which is defined by GCI, or grid conversion index. For computational fluid dynamics, the allowable maximum for the GCI is 1%. So my GCI here is 0.75%. And mass independency test is also conducted to determine your optimum mass. So the number of elements, the optimum number of elements to seek for. So it is also a way to validate that your simulations is well to go. Okay, this is a computational results. There are two graphs here, as you can see from the slides. There is one. The A graph is hydraulic efficiency versus the orifice basin ratio, and the B graph is hydraulic efficiency versus RPM. So as you can see from the graph A, we can conclude that as the orifice basin ratio increases, there is a decrease in hydraulic efficiency, and as well as in the hydraulic efficiency versus RPM graph. The optimum angular velocity for the turbine to operate is 300 RPM. Exceeds from the 300 RPM, there is a drop on the efficiency. And why is that so? Okay, for some of you who may be in mechanical engineering student, I'm gonna recall again about the turbo machinery. There are three velocity components in by the time the flow passes the blades. There are relative velocity, tangential velocity, and also absolute velocity. So ideally and analytically speaking, if you want your blades to harness all the energy carried by the water, the absolute velocity must be parallel to the plane of the blades. So the only parameter that determines the efficiency of the turbine is the relative velocity vector. So we definitely need to know the value and also the directions of the relative velocity. For my case here, as you can see from the figure A and B, 0.14 orifice basin ratio and 0.18 orifice basin ratio, we can see that there is the directions and the value for the relative velocity vector is the same. The value of the relative velocity ranges from 0.362 to 0.72. So we can see here from the initial velocity, the relative velocity here, prior to entering the blades. You can see the direction is still the same, right? Parallel to the blades, right? So there's no differences. So it indicates that relative velocity in conjunction with orifice basin ratio, there's no effect for relative velocity here. in determining the efficiency. And okay, this is the velocity vorticity contour. This is just to prove that the blades absorbs the vortex phenomena occur as a result of this flow. So the red signs here indicates that the vorticity, the vortex number is bigger because it's the red sign, the maximum value of the vorticity. And also it's also a sign that the blades absorbs the vortex here. Okay, honestly speaking, the effects of orifice basin ratio is directly to the turbulence occurred at the outlet sections of the blade. Why is that so? The turbulence partly comes from the shape of the turbine that I'm using. The turbine is straight type blade turbine, so it has a sharp corners at its tips. We all know that a fluid is sensitive to sharp corners, and it cannot turn to 90 degrees because sharp corners tends to create 90-degree angles for fluid to pass through. So as a compensation for that, we can see from this circulation here occurs. And the differences is the 0.14 ratio, the circulation is thinner, but for the 0.18 it's thicker. Why is that so? Because the orifice base or the orifice diameter is getting bigger. The bigger orifice diameter, the bigger circulation be produced. And what I mean is the fluid discharge is bigger and also results to the turbulence created because the intensity of the discharge fluids is getting bigger too as a result of enlarging the orifice diameter. This orifice basin ratio too. So that's why there's an increased from the 0.14 in turbulent intensity dramatically to the 0.15, 16, 17, and 18 because of the enlargement of the orifice diameter affects the turbulent intensity. We can also see from the contour of the turbulence.
I'm sorry for Mr. Syawali, your time is going to be up, so please make it faster.
Okay. So the conclusion is the orifice diameter affects the efficiency of water vortex turbine, and the computational result shows that a basin with orifice basin ratio of 0.14 produces the high efficiency at 65%, with the number angular velocity is 300 rpm. So this is the condition for my simulation. 0.0005 meter cubic second flow rate, and also the head used is 450 millimeter. So the decrease of efficiency is a result of turbulence existing at the outlet sections of the blade. So thank you very much for.
Okay, thank you for Mr. Syawali. Interesting study from Mr. Syawali. Maybe is there any question from the participants or audience? We have one question in. From Mr. Abdul Muiz. Lots paper recommends key omega SSD as turbulence model for some acceptable reasons in CFD analysis. Have you considered on this? Please, Mr. Syawali.
Wait, I can see the question. Wait, what happened? What is the question? Oh, sorry.
Lots papers recommends key omega SSD as turbulence model for some acceptable reasons in CFD analysis. Have you considered on this?
Before conducting this, I was using the same K omega SSD turbulence too, but in terms of vortex visualizations, there is some slight differences. So I pick the transport SSD because it gives the best representation of the vortex form here. I can see it from the relative contour. You can see it gives the best visualization of the vortex. So yeah, I pick the transition SSD. But yeah, before choosing this, I choose the key omega SSD, but it doesn't give me better visualizations of the vortex. So yeah, I choose the transition SSD.
Okay, thank you, Mr. Syawali. And the next question is from Rahmat Waluyo. How many cell zones you use to partition fluid domain, and do you use multi-friends frame to accommodate different velocity of rotating and stationary fluid domain? And what is your consideration when you decide to use transient model rather than steady one?
Oh, okay. It's pretty tough questions. But anyway, I don't use multi-reference frame to for the velocity rating standard club because I don't really understand about the. I once considered it, but it's too specific and it's too difficult. Though it gives you the best representations for the visualizations. So that's why I choose mesh motion feature than rotating in standard fluid domain. And also, so why transient model? Because steady to me, why transient? Because I've already conducted the experimental before, and no, experimental is still far away, but the experimental doesn't fit the representation for the steady. So steady means that your phenomena is steady. There's no particular changes on the phenomena. So I choose a transient over the steady because it represents the whole situation, the real situations of the vortex itself, rather than steady. That's my answer.
Okay, great answer from Mr. Syawali. Okay, this is first presentation from Mr. Syawali. Let's next to the next presentation from Mr. Hanapi Ali with the title is Numeric Evaluation of Minimum Residence Time in a Delay Chamber Using Scaled-Down Model. Please, for Mr. Hanapi Ali, time is yours.
Okay, thank you for opportunity. It's my screen clear?
Yeah, Mr. Hanapi. It's clear.
Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon. I would like to thank you for invite me to join with this conference. I will explain my research about the numerical evaluation of minimum residence time in delay chamber using scaled-down model. For the first, I want to introduce you what is the delay chamber. Delay chamber is the part or a component inside nuclear research reactor in RSG gas in Serpong, and this part is a function is to delay for the nuclide with the big emit radiation can be decayed before go to the other component. So what's this? What it's interesting for understand or for know the phenomena inside it, because in reaction fission in nuclear reaction with light water reactor like RSG gas in Serpong, interaction will be occur between oxygen and nitrogen. Will be oxygen and neutron, and will be generate the new nuclide nitrogen 16. Then it's very have a big radiation, but have a short time for the decay. The radiation is around 6.30 mega electron volt, and the time for the decay, half the decay is 7 seconds. RSG gas have a document for analysis before from the planning of building and after and operating. The document said the 50-second residence time of flow inside the delay chamber. So it's the time requirement, minimum time requirement for fluida throughout the delay chamber for the safety reason. And this is the geometry, the real of prototype. But if we back to the before presentation, the delay chamber is position is below the fuel storage pool. It can be described. It's not impossible to we access it. So where's the because that the impossible to access it, the best study for understand about the minimum residence time, we use the simulation code like CFD. But it has a big enough for geometry. So we must to scale down it for the for the minimize the mess. So inside the delay chamber is have a throttling plate or a perforated plate where the holes, the small holes. So if we convert it to the mesh, it will make this a big mess. So we must simplify it. Nah, this is a challenge to method to understand it. We have a 50-second resident time, not completed detail analysis report. So this is the big reason why we must study it, because the report of analysis safety is not incompleted, not completed by the calculation. And incomplete technical documents such as the detailed drawing of perforated plate, it's gone. And method to direct measure is expensive and almost impossible due to the position field. So we will apply the method using the CFD particle track. And we have the disadvantage for the CFD. The effect of discretization is bigger mesh, better accuracy, but the bigger power and longer time computing. And because that we need this to scale down model and simplification of geometry. In this case, we assumption as a porous media for perforated plate. And to ensure we have a proper mesh, we use grid convergence index study. For scale down model, we have a disadvantage like level similarity issue. Because that we applied the scaling user using proper scaling method like Isika Taoka, and this scale have been have been done by the other research in South Korea for his experiment. This is the method scale down model. We use the Isika Taoka method. From that we can find a key of parameter like a velocity inlet of the fluid. We can find the relationship about it. We can ratio of the length as a lambda, and the time model and the relation time model and time prototype to scale up the result from this simulation. The geometry and mesh simplification. We simplify the geometry to get the mesh for no longer simulation. So the perforated plate we assumption as a porous media. So we can get the parameter power get it from the manufacturing data for the stager arrangement like in the picture. This is the equation use it. And we can use the grid covariance index, where is from the study we get the very small. So, but the study above, study of the GCI for the fine medium size mesh has actual to extravert value for minus 4.6 with calculation error 0.0%. So we use the number of mesh is in number of mesh of 2 is around 2 million. A simulation that we use is have the minimum area size 2.57 and maximum at 5 with the total cell 2 million around, and with working fluid it's the same as prototype. We use water with the density 998.
Sorry, Mr. Ali, your time is going to be up, so please make it faster.
Okay, the result is can be we can
make
look
it faster, please, Mr. Ali.
Okay. So from the simulation we can get the concentration of the histogram of particle through the delay chamber, and we can get the time. So after we scale up, we can know about the error from the simulation and the real time 50 seconds is around error 10.09% from the real end model. So this is the conclusion, and thank you.
Okay, thank you for Mr. Hanafi Ali, great presentation. So is there any question from the panelists or participants? Okay, maybe I want to ask you a question. Okay, how confident and accurate your study to the real case, Mr. Ali? How accurate?
Yeah. After we scale up, in the simulation, we get this around mean time residence around 15 seconds, and after scale up, we need the equation for time like that, and we get of 55 seconds. So it's the error from the document of safety analysis is around 10% if we use it. So the simulation result is have around 10%.
Okay, thank you, Mr. Hanafi Ali. Maybe we can continue our presentation, and the presentation will be presented by Mr. Nur Ikhwan, where the title is GFD simulation for investigating the effect of coal size on tangentially coal-fired boiler combustion. Please, the time is for you, Mr. Nur Ikhwan.
Okay. Thank you for the time. Good afternoon, the audience. At this time, I'd like to present my paper with title Safety Simulation for Investigating the Effect of Coal Size on Tangentially Coal-Fired Boiler Combustion. As we know, most of power plants in Indonesia were designed for medium rank coal, but all of state power plant supplied with low rank coal due to economic consideration to reduce the operational cost. The change of coal requires a lot of adjustment to maintain efficient combustion. Some adjustment includes air-fuel ratio, primary air and secondary air ratio, coil size, and nozzle tilting angle. Previous study, as has been performed by Choi and Kim, show that a strong swell can prevent overheating on wall side of the boiler. As we see on the left side, so the swell performed by nozzle from the boiler. The strong swell on the bottom will be weaker and weaker on the upside of the boiler. As we can see on the right side, higher temperature occurs on the center of the boiler or furnace. It's so a variable here. So the swell will be weaker, but higher temperature will be reduced too. It means that most of the combustion of the coal perform on the center of the boiler. Second study performed by Belosevic. He varied secondary airflow and investigate the combustion temperature. As we can see at the standard operating condition on the circle symbol here, the temperature is increased from about 800 and maximum. If the airflow is reduced to 20%, it will increase the temperature, and if the secondary airflow is increased, the temperature will be reduced. The next study performed by Sridan that investigates the variation of coal size. On the right side is the fine coarse coal, and the left side is the fine coal. As we can see on the bottom contour, temperature contour, temperature the near wall project. We perform a similar simulation on the power plant. We take case in PLTU Pacitan. We use the geometry from the actual condition, and if we can see on the right side, there is the boundary condition for the furnace. There is inlet for coal and air, primary and secondary, and there are some changer starting from the simulation condition or operating parameter condition. The plant has a load of 300, around 400 ton per hour. Secondary air mass is about 767 ton per hour. Whole mass fluid is 150 ton per hour, and excess air about 12.9%. The coal modeling performed by injection, with the number of injection for each burner is 10 particle, and the type of particle is combustion process, and the material for the coal is coal with medium value. That this content has been changed into low rank coal value. The average distribution is Rosen-Lemler and flow rate about 3.68 kilogram per second. There is the range of the coal size from 700 micron until 250 micron. This is the reaction for the cold combustion. There are 6 chemical reactions during the combustion process. This is the simulation setup for modeling. We use K-epsilon standard turbulence model and use porous medium for heat exchanger. Wall tube was modeled as solid wall with heat absorption that previously calculated from heat transfer process. Conversion criteria for 10 power minus 6 and pressure velocity coupling use simple, and cold particle modeling use solid injection with combustion. There are 2 variations for the simulation: cold particle size, 74 micron for design condition and 35 micron for actual condition. And there is also 2 tilting angle condition, 0 degree as a design and -5 degree as an actual condition. From the first simulation, use 0 angle degree. Left side is combustion for 70 micron cold size, and the right side is for 35 micron. As we can see, using smaller cold size cause most of coal was combusted on the heat exchanger area. This is not good because it can cause overheating on all of the heat exchanger, especially for superheater. From the temperature contour on the same condition, we can see that smaller coal size cause higher temperature on the all of the area of furnace. This condition can lead to overheating on upper side on heat exchanger, and on the lower side, the wall tube can be harmed by overheating, since high temperature occurs on the wall.
Sorry, Mr. Nurihwan, your time is 1 minute left.
Yes.
Your
okay.
time is 1 minute left.
1 minute, okay. The second simulation use -5 angle, same condition. The small size coal cause overheating on the upper side of the furnace because of furnace will furnace on the upper side. And the same condition on the -5, high temperature still occurs on the wall on the boiler. It can be concluded that operating boiler at -70 micron coal size will produce high temperature in the center of furnace, and most of coal are burned after FAKT. Operating boiler at 35 micron coal size will produce high temperature near wall furnace, and most of coal particles are burned after entering flue exit gas temperature or FAKT area. Nozzle tilting angle value 0 and -5 has less significant effect on coal combustion. Okay, that is my presentation. Thank you for the attention.
Okay, thank you, Mr. Nur. Nice presentation from you. And is there any question from the participants or audience? Okay, maybe a question from me. Is it can be used for from the different ambient condition, Mr. Nur? Your study, I mean. Is your study can be used or can be used in different ambient condition of the chamber?
Different condition for
different condition of ambient of condition in out of the chamber.
Yeah, we have a condition where the boiler has been operated and have been in operating temperature. So we use steady condition. That means that the furnace is hot enough to be operated on the loading. So that anything that affect the operation is temperature condition for air inlet and cool temperature. So we use the actual condition for the simulation.
Okay, thank you, Mr. Nur.
Sorry, Mr. Willie, I think there's, I don't know if there's time, but there's one more question on the chat box from Mr. Achilles Hermawan. The question is, how do we ensure that the scaling is suitable enough to represent the real reactor? What are the main parameters to be subjected at first? Perhaps Mr. Nurihwan, there's a little time, but can you please answer the question if you could?
Okay. We model we use simulation, so we use a real size of the boiler. So there are no scaling, yeah, including the flow rate and velocity of air and cool. We use actual size. So there is no scaling, I think, because we use simulation.
Okay, thank you for Mr. Nur. Yeah, thank you for Mr. Nur Ikhwan. Okay, let's continue our next presentation to Mr. Kevin with the title of his presentation, Effect of Chamberlain Variation of Open Flume Turbine Performance. Okay, the time for Mr. Kevin.
Yeah, wait a minute. So yeah, allow me to introduce myself. I'm Kevin Kamaswara from University of Indonesia. I'm from the Pico Hydro research team from the Department of Mechanical Engineering of University of Indonesia. And today I'll present my study on effect of Chamberlain variation on open flume turbine performance. Indonesia has 1.1 of population that is still not get enough access to proper electricity, but our water energy potential is 93.4 gigawatt. That is the highest potential after solar power. Why does this matter? Because water energy, unlike solar energy, depends less on the condition of the environment. So, and cost, and about cost, it's a bit more efficient. So that is that. So Indonesia has a water energy supply. Indonesia doesn't. Most water supply energy is not really that of a high head. This turbine, this open flume turbine, which requires less head and more of a flow rate, is more optimum to this kind of matter. So open flume turbine is basically a propeller turbine, which is the same type as the Kaplan turbine, that has an open casing, open spiral casing, unlike the propeller, and it has what's fixed blade thing that is different from Kaplan, because Kaplan turbine can vary its blade angle. So open flume turbine also have a range of power that is less than 5 kilowatt, which is very fine if we are going to supply a lot of energy to the eastern side of Indonesia, which doesn't, especially the village area of Indonesia. So that is that. So now about this study, focused on comparing the variation of Chamberlain. Most of the research on Kaplan and propeller turbine focus more on the profile, that is on the blade number. and less on the profile of the blade itself. So here we come to to compare the effect of our camber line. That is, we're trying to compare the control vertex, which is a geometrical feature to control the shape of a curve, controlling the end of slopes. So it's like, you know, the slope of the curve is equal to the slope of the triangle, the given geometry, and the interpolation is the curve is trying to fit into the point, the given point. The difference from the control vertex, but is that control vertex focus on angle and the interpolation is focused on the place, the point. So that is that. Now, this study compared the performance of a runner, of an open flume turbine runner with control vertex, camber line, interpolation camber line, and zero camber line. So the method used is that we compare an open flume turbine with head of 2.71 meters of rate RPM of 1,400 RPM, and with a specific speed of Q of flow rate specific speed that is 220 using Simpson's method. The blade is designed. The triangle is designed using Patrick Hyen's method of designing a velocity triangle, and the velocity triangle is made into a camber line. Now, the camber line used in this study varies. That is, first of all, the first is the A1, the camber line that is made by control vertex, and the second is the interpolation camber line, the camber line that is made using interpolation feature. The third is the zero camber line. The software used, the analysis used this study used ANSYS Fluent 18.1 on 3D analysis. We use steady state, and the mass inlet flow is that 109. We are choosing that because then as what you're using that so that it fits the condition on the site that we have on open flume turbine, and the pressure outlet is 0 Pascal gauge. We do the Richardson method of GCI, grid convergence index, that we compare the mesh, the number of mesh, to get the which mesh that we use, which mesh will we use. So we compare then 3 numbers of element, and it is found that the difference between the result of mesh number 2 and mesh number 1 is quite different, not so much. So we use the mesh number 2 to our calculation to minimize the time needed for calculation. So here's the thing. Here is the method used. So we divide the blades into 3 sections. First of all, so that it is easier to get the result. And
sorry, Mr. Kevin, your time is 1 minute left.
Okay. So the result is this. This is the geometrical result. The combination varies. The airfoils also varies. The runner output, which we get that the thing with interpolation method, which has the highest camber, it has the highest camber that is more curved, the most curved is what has the higher performance. That is that. And pressure counter and it's like this. The B, the interpolation method has more pressure difference, which contributes to higher lift, which could contribute to the higher performance. And this is the pressure distribution. We could see that the B1, the interpolation method, has the highest difference in differential pressure. And here the velocity profile. Yeah, we could see that the interpolation method has quite higher pressure velocity difference. So that is that. The conclusion is that the power output of the interpolation is highest, and the power output of the zero camber line, which is not the less cambered, is the lowest. So that is that. Thank you very much.
Okay, thank you for Mr. Kevin for your presentations. Okay, maybe is there any question from the attendants or participants? If it's not, I will ask you two questions. First, how accurate your study to the real case? And second, what happens if the mass inlet is changed?
Well, if the first thing is that the accuracy of this study, the accuracy of this study is, well, I'd say it's well, according to the Richardson method, it should be fine. But this result is, pretty aligned with the theory, the general knowledge that the more chambered foil, an airfoil, the higher lift will it get, as long as it doesn't hit the stall point. So, and in case of velocity triangle, this kind of the angle of the stall angle is not really that. It rarely hits the stagger angle because the triangle is designed to for it to make the optimum. Depends on the blade if the inlet is increased so that the stall angle is surpassed, that would make a different different result. It would minimize the result because there would be negative. To comply with that, we need angle based on the inlet mass flow. That is my answer.
Okay, thank you. And there is a question from Mr. Abdul Muiz. How you develop the chamber line, especially the high one? What is the main parameter that you control to develop it? Please, Mr. Kevin, you can answer this question.
Pardon me?
How you develop the chamber line, especially the high one? What is the main parameter that you control to develop it?
So the interpolation method, the highest one, we use, the in SolidWorks and Autodesk Inventor, that there is a curved line, right? That it specifically says that interpolation method, that is a curve that fits into the the selection point. It's just like the interpolation method in Excel and things, and that is that. So we develop the triangle using velocity triangle, and we fit our curve into those lines using interpolation method. It is available in design software, such as Inventor, Autodesk, AutoCAD, or SolidWorks.
Okay, thank
That
you,
is my
Mr.
answer.
Yeah, thank you, Mr. Kevin. Okay, let's continue to the next presentation from Mr. Sin Helen with the title Design and GFD Simulation of Centrifugal Compressor for Mini Jet Turbine Engine 200 Newton thrust. You have 8 minutes to present your presentation. Please, Mr. Sin Helen, the time is yours.
Okay, thank you, Pak Willy Prasida. Okay, Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Sin Helen Dinara, and Pak Muhammad Agung Brahmadja is my supervisor in mechanical engineering from Gajah Mada University. And today I'm going to present you about my research in design and CFD simulation of centrifugal gas compressor for mini jet turbine with thrust about 200 Newton. Again, the background is we are living in Indonesia, which is an archipelago country. This is consists of more than 17,000 islands. That's of course need a great defense system to maintain our territorial integrity. The defense system equipment is one of them is missile, and missile is using propulsion system. That the turbojet engine is one kind of missile propulsion, and we are now talking about mini jet turbine with it will be integrated to missile for its propeller. And in designing, we have several challenges that we have to able to decide, generate design parameters such as pressure ratio, mass flow, and axial speed. And we also have a challenge to reduce the cross-sectional area to reduce the drag. And also we have a challenge in tangential speed, which is this is limited because of we are using material compressor wheel is aluminum. And the objective is we are going to research on design and simulation of the compressor, and this will be the target is to obtain the best compressor and diffuser design, which is can produce 2.66 pressure ratio and 0.53 kilogram per second for mass flow rate. We have to reach the best diffuser and diffuser design, which is can regulate the axial air velocity about 30 to 60 meters per second to ensure the all of the fuel is completely burned in the combustion chamber. And then this is the research methodology that we are going to define the some parameter, dimensional parameter in compressor, diffuser, and our constraint is like we previously described, pressure ratio, mass flow rate, and speed. And finally, we're going to have a pressure predicted curve, which is indicate the pressure ratio and mass flow rate. And this is the operating condition of our reference research, which is conducted in Padova University, which can generate a gas turbine engine with 200 Newton power. And we have our study is we are having two models to make a variant. The first model are radial, and the second model is backswept compressor. All of the data is described here, and this is for the typical drawing for the radial on the left side and the radial compressor on the left side. Right side. And this is the modeling we are using as Autodesk Inventor. We are using modeling, and we also created in fluid domain. And then for the simulation data, we are using multiple reference frame, which is the model is 110 or 36 degree, and this number here. And the mesh quality, we have acceptable mesh quality, which is aspect ratio, orthogonality, and skewness. And also the minimum and maximum angle is within the acceptable range. And the simulation data, as we can see below, we are using transient. And we also for using viscous model using K epsilon. For the material, we are using real gas Huang. The method is simple. And the iteration number is about 5,000 up to 50,000 iteration. It depends on the stabilization of the graph. Okay, and the simulation data, the boundary condition is as described here. And then for the simulation step, this research we are running about 30 simulation. Each model has 15 simulation, which is we vary the speed and also vary the mesh flow as described here. We have 3 speed, 70,000, 85,000, and 100,000. And this radial and the except compressor. And the validation we're doing by residual convergence. We have to reach the stable residual continuity, and we have also value consistency, which is pressure ratio. Is we have to maintain the consistency in one value. And the mass flow inlet and outlet difference, we make it a flux report so that the error is very small, it's about 0.007%. And the mass independency test, comparing to other typical research to have more confidential in confidence in our research. And this is the simulation data. We're going to here is the stable flat compressor pressure ratio graph. And the validation for the analytic validation, we're doing the calculation, and we have the calculation. We have the pressure ratio is 2.52. It means we have 5% error. And for the typical research experiment validation, we have our simulation compared to the Padova University Italy is the error is about 0.02% error. And we're going to CFD post, and the CFD post. This is the pressure distribution. The pressure distribution, the left side is the radial impeller, and the right side is the back sweep. We can see here at the outlet, on the outlet pressure, we maintain at 2.6 atmosphere, and the inlet is variable. And as we can see here, the suction pressure in the radial impeller is less than back sweep. It means that the pressure ratio in the radial compressor is higher. And the pressure ratio is here is 2.86, while the back sweep is 2.66. And this is in line with the density distribution. It's about the same with the pressure distribution. This is in the in that area is less in density, and then in the discharge area is higher density. And as compared with the back sweep, is the radial is have more bigger range. And this one is the as I described previously, that at the same speed and the same mass flow rate, the radial impeller has a bigger compression ratio, but the efficiency is lower. And this is the velocity distribution. As we can see here, we have a radius area in the tip of impeller of the radial impeller, because of we have the tangential speed is higher because of the degree backswap angle is 0 here, and then the tangential speed will be higher in radial. That's why it's consume more power to drive the compressor. And compared to the backswap, it's less speed, and then the power is also less. That's why the power required to drive the compressor is less, and then it will be impact to the efficiency of power. And we go to the important parameter, which is axial velocity. That with axial velocity, we have to maintain less than 60 meter per second to maintain and ensure that the fuel will be burned completely in the fuel, because of we going to faster than the September range, then the fuel will be burned in behind of the turbine, and this will be danger for the flame will be burned in outside of the turbine. And by the simulation, we have the radial has higher speed, about 55 meter per second, and for the backswap we have 51 meter per second. And we have also the swirler. The swirler is the swirler. The swirler works well by directing and stabilize the airflow, so that the airflow goes well, and the air goes smoothly to the combustion chamber. And now going to the data analysis, and we have, as we can see here, the power here is the generated from the torque multiplied by omega, or speed. And we can, as we can see here, we can show that the backswap impeller has less power to drive, less power required to drive the compressor. And then we go to the centropic power. This depend on our state of condition, and it will be use this parameter to define the efficiency, eccentric efficiency, which is the eccentric power divided by actual power. At the chosen point, chosen speed 85,000 RPM and 0.53 kilogram per second. The backswap compressor, backswap blade has efficiencies higher, which is 88.7%, and the radial compressor less than 75.4%. And finally, we have the mass flow rate, the performance curve. We are here, and we can see here the curve is for the backswap is steeper. The steeper curve is mean that good instability, and we have also wider range of operating. Can have and we have also search for the search area, search point is more safe, because we are, as we can see, the point of the operating point is in the negative gradient. Negative gradient, it means it in the safe from the search, while compared to the radial compressor is located at the positive gradient, which is the area of searching. Okay, and the conclusion, both of the model can generate the pressure ratio and outlet axial velocity at the mass flow rate in accordance with the objective of this study. And the radial blade compressor model can provide higher pressure ratio at the same speed, but unfortunately it has lower efficiency. And the next conclusion is the backswap compressor model is operate at better operating point from possibility of surge. It's better than radial compressor, and The backstrap model has a better performance. The better performance here is defined as the lower power consumption and steeper performance curve, which is more stable, and also lower compressor outlet axial velocity. And the next conclusion is the smaller cross-sectional area of the compressor. We need, then we have to increase the rotational speed. And at the last is the rotational speed chosen is here is 85,000 RPM because of the tangent speed. This point is very close to the maximum allowable speed for the aluminum compressor wheel, which is 440 meters per second. This is my presentation, Pak Willy Prasida. Thank you. And
okay, thank you for Mr. Sin Helen. Good presentation from you. There is a question from Mr. Abdul Muiz. Why K epsilon is chosen as turbulent model?
Yeah, here guys, we have several study literature in the same typical research, and most of them is using this model. And we have also simulated with another method, but the best method is K epsilon. This is some solution is divergent, and by this method we can go to the simulation and simulation is goes well. Thank you.
Okay, thank you, Mr. Sin Helen. Okay, let's continue to the last presentation from Mr. Muhammad Suban with the title is Determination of Absolute Roughness under Transient Condition in Gas Transmission Pipeline. Please the time for Mr. Muhammad Suban.
Okay, thank you, Mr. Moderator. Can you see my slides?
Yeah, we can see your slide clearly.
Okay, thank you for allowing the time for me to present my research that has been conducted under the supervision of Dr. Dinda Rianto and also Professor Indarto from the Department of Mechanical and Industrial Engineering, Universitas Gadjah Mada. So before moving into the detail, I would like to give you some general picture about the problem, which is the gas transmission pipeline. If you see the picture here, there is a pipeline that represented by black lines here, and it is a gas transmission pipeline, which is a pipeline that is designed to transport a certain amount of natural gas from production site into a consumer market. So the amount of fluids, which is natural gas, that transported within the context of this research is 0.2% of country GDP. And it brings us into a 5% contribution to GDP because that amount of natural gas will be used by industry to produce some goods and a service. And 5% is quite large because it is larger than GDP of 129 countries in the world. So it served the dense market, which is 1.3 times of Java in terms of populations. As we know that Java is the most populous islands in the world, and at particular region, which is the western side of Java, the population is even higher, which is 1.3 times of the entire island population. So it's a really dense market. And also, as Professor Nathan mentioned earlier this day, efforts to decarbonize the energy source, while renewable source is still far from the target for Indonesia, natural gas provide transition into a renewable, because we know that natural gas is the lowest carbon fossil fuels. And on the right side of the presentation, you see the schematizations of actual transmission pipeline. So the transmission pipeline is operated by gas transmission operator, and they need a model to predict the unforeseen event that caused by change in flow rates or pressures that may be induced by the consumptions or any disruption on the supply side. And in order to construct the model, we need absolute roughness, which is the most common tuning variable for Colebrook-based model. We also need to compromise between computational time and also the accuracy. So the model should have a short computational time and also feasible accuracy. And the absolute roughness can also be determined by feeding the operational data by steady state model. But actually, in the long transmission pipeline, the steady state data is not available, is not easily available. And so it is proposed to use transient model instead of steady state model in response to the feasibility of the data and also the use of the model, because we want a model to be responsive in change of flow rate or pressure on the boundary. So this is some snaps on the transient behavior that happens on the transmission pipeline. I capture on top 3 boundaries, which is cover like 70% of the total flow rate of the pipeline. So I hope it give you some representative idea. The flow rate is highly fluctuate. It differs between boundaries, but if I emphasize on the green flow rates here, it represents the usage of a power plant that use natural gas to compensate their peaker needs of electricity generations. And on that flow behavior have an effect on pressures. As you see in the right side here, we have a fluctuative pressure that follows any change in flow rate, and the transmission operator need to maintain the pressure above the minimum requirements. Because if the pressure falls below the minimum requirements, then we consider the gas transportation is failed. So what is absolute roughness? So in left side, we see a popular graph by Moody that based on his research on the 1944. We still actually use this research of Moody until today to design any fluid pipeline. Okay, so from the conservation of for the transient model, we use conservation of mass and also conservation of momentum. And the conservation of momentum, we can see an F here. F is friction that is represented also in a Moody diagrams, which is depend on the relative roughness or epsilon per d. And this Moody diagram also can be transformed into implicit equation, which is Colebrook equations. You may see the F notation here and also epsilon. So we will use these Colebrook notations, Colebrook equation to complete our model. So the absolute roughness itself is not really how the pipe wall protrusions in real condition, but it represents uh, the Moody experiment here. Isn't we can't really measure the relative numbers when a pipeline is really in operations. So we estimate based on this model.
Sorry, Mr. Subhan, your time is 1 minute left.
Okay, so this is the data. We have a elevation profile and also the pipeline data as well. We have a offshore segment and also onshore segment. And this is the steps. Let's skip to the results. So the results that indicate we can have a optimal. We have the roughness that close to the real data on the field. So if I compare the roughness that supposed by Moody diagrams, by Moody experiment for the pipeline, which is 0.0018 inches, we have a large discrepancies between real and simulations. And after tuning, by changing the roughness into lower roughness, we see here we have a lower discrepancy or better accuracy. So we conduct the simulation on a 5-year basis, and we see that the roughness is changing along the year. For the 2016 to 18, the roughness seems to be lower, decrease, and after that it increased. We observed that because there was a cleaning peak activities. Cleaning peak is we put an apparatus into a pipeline and push that to push the liquid and also debris within the pipeline. So cleaning peak activities is the main cause of the decline of the roughness. And after that, we don't do the cleaning peak. So we observed that after 2018, the roughness is increasing. So the conclusion after the study is for a new pipeline, initial absolute roughness value is 0.0024 inches can be used as a reference instead of 0.0018 that usually used by engineers to design the pipeline. And also absolute roughness of a new pipe, because there is a manufacturing technology improvement since Moody time into nowadays. So there is a research that observed this change in roughness regarding the manufacturing technology. And cleaning peak is necessary to enhance pipeline transport efficiency, and the increase of absolute roughness observed for the time when there were no cleaning peak activities is 0.001 inches per year. Thank you.
Okay, thank you for Mr. Subhan. Great presentation. And there is a question from Mr. Abdul Muiz. Okay, the question is, does possible to apply this method to the other type of fluid?
Well, on the non-compressible fluids, such as actually I'm not I haven't conducted any experiment on different fluid, but regarding the physical phenomenon, this is also could be applied to another fluid, as the model is global, and on the Moody experiment it is applied to compressible and non-compressible fluid as well. So maybe the difference is on the equation of state, which is applicable in compressible fluid.
Okay, thank you, Mr. Muhammad Subhan, for your answer. Okay, this is the end of the session, session 2 of the presentation. Thank you for all presenters for your presentation. Next session will be going to Professor Wolfgang presentation. So the time is for MC, we'll be back to the MC.
Okay, thank you very much, Mr. Willy Prasida, for moderating that paper presentation session. And also thank you so much to the paper presenters for their amazing presentations with very interesting topics, as well as for the participants with all the amazing and interesting questions and opening up very, very enticing discussions. So right now we have arrived at our third and final keynote presentation for today, which will be delivered by Professor Wolfgang Polifka. However, before we jump straight in, please allow me the privilege of introducing our moderator for this session, which is Professor Harwin Saptoadi. Professor Harwin, can you hear my voice?
Yes, I can hear you, your voice clearly.
Okay, so whenever you're ready, sir, this session is yours. So I deliver the time and platform to you. So please do, Professor Harwin Saptoadi.
Okay, thank you very much for the organizing committee for giving me a chance to guide the afternoon sessions, yeah, for the last keynote speech for today, which will be delivered by Professor Wolfgang Polifka from the Technical University of Munich or München. I see that Professor Polifka has already been here, and well, very good afternoon, all honorable conference participants. I really hope that you enjoyed your lunch and enjoy the 11th Thermofluid conference today and tomorrow. Let us begin the afternoon keynote speech session of the conference. Well, however, special for Professor Polifka, I wish you a very good morning, a very nice morning, because I believe that it is morning right now in Munich.
Yes, it is. Good morning.
Yeah, good morning. Yeah, again. Thank you so much for accompanying us in this annual conference and delivering an interesting keynote speech for all of us. I do hope that your oral presentation, although delivered virtually, will inspire us to perform better and better in the world of energy engineering. Well, without any delay, please allow me to show you previously the biodata, your biodata, Professor Polifka, before you begin your speech. Okay, let me share. Well, I have. Please wait a minute. It takes a while to open the curriculum vitae. Okay. Oh, I cannot find it somewhere. It has been opened successfully, actually, but I don't know how it is. It doesn't appear in this screen. Could you please the
Professor
organizing
Harwin?
committee?
Yeah. Okay.
Yes.
Maybe I can help you open
Yes, please.
Professor Polivka's CV.
Yes,
so
please.
if I could, I will share my screen right now. And can you see?
Yes. Yes. Okay. Thank you very much. Okay. Well, Professor Wolfgang Polivka, PhD, an associate professor from the Technical University of Munich or München from the Department of Mechanical Engineering. Well, his research areas are fluid mechanics, CFD simulation, numerical analysis, system modeling, CFD, again, numerical simulation. Well, aerodynamics, engineering thermodynamics, modeling solution, and numerical modeling. Another highlight of his is the education. He was actually a physicist. I mean, not physicist. He studied physics.
True.
He studies physics in the University of Regensburg and University of Colorado Boulder in the USA, and City University of New York, also in the USA, in physics, 1999. And he got his PhD degree also from the City University of New York with the dissertation topics, aspects of helicity in turbulent flows. He has worked as a research assistant in the also CCNY in Stanford University as well after his involvement in the CCNY and APP in Switzerland. And finally, from 1999 up to now, he is a professor at the Department of Mechanical Engineering at TU München. He got some awards and he experienced also in journal editors. And lastly, please then the next slides. I'm sorry that I can only mention some most important things. Yeah, he mentioned here only 8 papers, but actually I believe that he has written a lot more. We can see that from his age index. Yeah, it's index in Scopus. Okay. Professor Polivka, you will have around 30 minutes for presentation and immediately followed by Q&A for around 15 minutes. The title of the speech is Thermoacoustic Combustion Instabilities. Okay. And
right. Thank you.
Okay, please, time is yours, please.
I started my screen sharing, so you should see the title with a little animation looping. First of all, thank you for inviting me to contribute to your meeting. It's an honor. I would like to be in Indonesia today. I'm looking out at a very gray and dreary November morning in Germany. The sun is nowhere in sight. Temperatures is a little bit above 0 degrees Celsius. I'm quite confident it would be different at your location. So I will present thermoacoustic instabilities. That has been my major research topic since my time at ABB Corporate Research in Switzerland. That is for more than 20 years. And I would like to share my fascination with this phenomenon. It's very interesting in its own right. It's also very important for combustion technology. And although there has been a lot of research going on since the 1950s and then renewed activities in the 1990s and 2000, there are still discoveries, fundamental new discoveries in this field. What you see on the animation down here in the lower right corner is such a thermoacoustic instability. You're looking on a flame, a premix flame. So from the left here, you see my mouse. Maybe mouse is moving on the, oh, sorry, that wasn't what I tried to do. So there's pre-mixture of fuel and air flowing from left to right. And this flame develops an instability. So you have a fluctuation of the flow through this orifice, which serves as a flow holder. And if you look at the pictures on top, these are pressure traces of acoustic waves traveling away from the flame towards the upstream and the downstream side. So we have here an interaction of thermo, heat released by the flame in an unsteady fashion, and acoustics, that is waves propagating. And this interaction, as you can see here, from a state that is initially in rest, amplitudes grow very, very quickly in just a few cycles of oscillations to very significant magnitudes. And I wanted to show you this movie here. Perhaps you've seen it. It's from the 1950s, the Tacoma Narrows Bridge in someplace northwestern United States. This is discussed in many physics textbooks as an example of resonance. However, that is, in my opinion, not correct. It should be described as an example of self-excited images. I leave this movie running. There is a man trying to save his dog and all sorts of dramatic things occurring. I stick to the science and try to explain. Resonance you would have if the wind that is hitting the bridge would have a certain frequency, if the flow velocity would not be steady, but would have a frequency that is close to one of the mechanical eigenfrequencies of the bridge. And then the bridge, due to this unsteady forcing, can respond, and the closer you are to the eigenfrequency, and the less the damping, the larger the amplitudes will be. And in this case, you might have something happen. It looks much the same as what the movie is showing. However, in this case, the wind was not modulated. The wind was flowing pretty much at constant speed. And what happened is that a feedback interaction resulted in instability, which eventually caused the collapse of the bridge. So the important thing about self-excited instability is you have interactions of feedback, interactions in feedback, that starting from infinitesimal small perturbations can grow into large amplitudes and eventually lead to destruction of a system. And in the case of the Tacoma Narrows Bridge, the feedback mechanism was purely aerodynamic. The bridge had these large girders on the side, creating recirculation zones, and any displacement of the flame in the upstream or downstream or torsional displacement, as I indicated in the sketches, would give rise to net forces. So although the flow is steady, a small initial fluctuation gives rise to forces that enhance the small initial fluctuations, and eventually amplitudes grow and things go unsteady. Here is another nice example that I found on the internet. The Millennium Bridge opening in 20 years ago. This is also a suspension bridge, and you see lots and lots of people walking across it. And what's happening here is a case, again, of self-excited instability, but now it's biofeedback, because here it's the action of the structure of the interaction of the structure of the bridge with the people walking across it. And you see people are swaying left and right. They're sort of trotting along the bridge. The bridge is very crowded. Nobody can walk at his or her own pace, but you fall in step with your neighbors. And this sets up, again, a feedback loop, which can produce instability. And eventually people started panicking because they felt the bridge might collapse. It didn't collapse on that day, but it was closed and was renovated. And initial damping elements were installed that would eat up vibrational or oscillatory energy and result in damping. So it's again a feedback. There is a time lag here because the way the people respond to the oscillation is not right away. They try to counterbalance that the deck of the bridge is moving. But of course, there's a little delay, and these little delays are quite crucial. You might think of actually a child on a swing. A small child on a swing, I've seen with my own daughters. they see the big children going large amplitudes swinging, and they see that the kids are moving their legs in order to get the swing going. So they sit down, they move their legs, and nothing's happening. They're very frustrated, and they start crying. Eventually, they get the hack. There needs to be a precise synchronization with a certain time lag, such that you stick your legs out as you're all the way on the top of the cycle, and then you pull them back in as they're coming down. And once you get that, once you have this synchronization with time lag, instability, and in the case of a child in the swing, a very pleasant effect, of course, can happen. And the same thing can happen now to flames. And let me try to explain what's happening here with flames. What you see is a flame in a combustor, and we have a Q dot prime. The prime indicates something is fluctuating, something oscillating. And that generates sound waves. And the flame is expanding, contracting, expanding, contracting. That generates sound waves. And the sound waves are reflected here at the ends of the combustion chamber, and they travel back to the flame. Flames respond to acoustic perturbations. In particular, they respond to the velocity perturbations that is associated with acoustic waves. And they can set up a feedback cycle, and that feedback cycle can go unstable again if the time lag is correct. Timing is everything in those things. You can develop a thermodynamic interpretation of this phenomenon. Here you see a PV diagram as you know it from your engineering classes. Acoustic waves as such are isentropic. So if a wave is compressing and expanding a fluid element, it basically moves up and down an isotrope. That will be shown by the blue line here. Now, if you add heat and subtract heat as the element is being compressed, you end up with a cycle as shown here in red, 1, 2, 3, 4 with a single prime. Here, as I said, you're adding heat as you're compressing, you're taking heat out as you're expanding. So you would have shown here on the right, heat release fluctuation in phase with pressure fluctuation. In this case, you get a cycle in the clockwise direction. That is a cycle that generates mechanical energy, much like a combustion engine. The opposite case, where the fluctuation of heat release is out of phase, gives you a cycle that actually consumes energy, mechanical energy, rather than producing it. This is why feedback is so important. And here you have thus the relation between the velocity fluctuating, which controls the response of the flame, that's the Q prime, and then the phase with the pressure, which controls whether the cycle generates energy and possibly create instability or not. And this basic phenomenon was understood as early as late 19th century by Lord Rayleigh. And you find a mathematical expression of this on the bottom. Now, maybe, hopefully, you agree that thermoacoustics is fascinating. This picture shows it's a gas turbine before and after a thermoacoustic instability occurred. That it's also a topic of great technological significance. Lean premix low emission gas turbines for power generation or propulsion can exhibit instabilities. Rocket engines can, even heating systems can. And with the switch to new fuels, with a switch to carbon-free economy, combustion of hydrogen, and so on and so forth, we expect increased occurrence of this phenomenon. It's not new. I mentioned this before. In the 1950s, 60s, there was a lot of effort by NASA to control combustion instabilities with tremendous effort in the Apollo program. The F1, the Saturn rocket engine, had several thousand tests. Now, these days, of course, nobody wants to spend as much money as they did back then. So we rely on simulation to describe this case. And how can you describe and model? Well, you need combustion in a compressible flow. You need resolution of phenomena like mixing of fuel and air, transport of fuel from an injector to the flame, release of the heat, interaction with acoustic waves. So LES computation, in principle, can describe all these phenomena. However, I would caution you, it is not always easy to understand what is happening from large eddy simulations. There's so much happening here, 10 to the 8 degrees of freedom, that often to understand really the important feedback interactions in cause, what is cause, what is effect, what is input, what is output. That is often difficult to understand just from LES. So we actually use an approach that combines both high fidelity LES and low order model with paper and pencil models. And here is a guiding principle. It is credited to Einstein by some people, but so many things are credited to Einstein. I don't know if it is true, but let me show you in any case what simple models of thermoacoustics are and how they helped us to come to a discovery of a fundamentally new effect in recent years. So here is again this picture that I showed previously with the flame in the combustion chamber and the plenum, which is meant to be a source of oscillation in a resonator. And the traditional thinking was this thing behaves much like a flute. In a flute, you have a resonator, and if you blow across the mouthpiece, you generate some vortices, and the vortices can couple with the acoustic eigenmodes of the flute. And then by closing and opening holes, you change the possible wavelengths and frequencies of the eigenmodes that can exist, and thereby you change the pitch of the note that you're playing. But the important thing is, whatever the sound generation mechanism is, it couples with one of the acoustic eigenmodes. And for a long time, it was thought that it's just the same in a combustor also, that the flame can only excite one of the acoustic eigenmodes of the flame. And so you have a handle on the frequencies and the mode shapes, on the location of pressure minima, pressure maxima, and so on and so forth. But actually, that is not the right way of thinking about it. And here is a diagrammatic way of representing the interactions. This representation should remind you of control theory. Here you have signals going from one node to another. You have a direction of cause and effect, of input and output. So what this diagram shows, for example, is a wave here traveling from left to right. We call this wave FU. F in our notation is traveling from left to right. G is traveling from the opposite direction. Now, this wave, as it hits the flame, there's a bit of transmission. It generates a wave going also downward in this direction. That's the FD, F downward. And it is a little bit reflected, so there is a little bit of a wave G traveling in the upstream direction again. And the same if you have a wave coming here from the bottom, from the right side. There is transmission through the flame, and there is partial reflection by the flame. This would be happening simply if there is a temperature discontinuity in mean temperature. Now, if you add unsteady heat release, the flame expanding and shrinking, a monopole source of sound, this sound source contributes to the outgoing waves. So you have a contribution to the outgoing wave FD, you have a contribution on the bottom to the outgoing wave GU. Okay. Now, this heat release is caused by velocity fluctuations. So I give the cause to that effect, which is fluctuation of velocity through this orifice, through the flame holder, results in some complicated fashion described by what we call a flame transfer function, capital F here, in fluctuation of heat release. And again, this U prime does not come out of nowhere. It is governed by the acoustic waves that travel back and forth across the flame holder. So now we have a diagrammatic representation of the causes and effects in this system. Now, if you look at it closer, you see, wait a second, there is a feedback loop here, a local feedback loop, or an intrinsic feedback loop, as we call it, which does not involve interaction at the exit. Interaction that does not involve reflection of the acoustic waves at the exit or the inlet here. Okay, that's why we call it intrinsic. It's really confined to the immediate vicinity of the flame. There is again a fairly simple analogy here. You know electroacoustic feedback in a concert hall, right? You have a speaker, you have a concert hall, and if you crank up the volume too high, or if the concert hall does not have enough soundproofing, you may have a feedback that gives this terrible sound, which is not pleasant. Why? Because the microphone picks up what is reflected by the concert hall or the room. Our intrinsic feedback would be nothing but also known from whoever set up a stage once for a band, perhaps. If you place the microphone too close to the loudspeaker or right in front of the loudspeaker, you can have a direct feedback from the speaker to the microphone back through the cable that does not involve the acoustics of the environment. In that sense, that is what the intrinsic thermoacoustic feedback loop is about. And although this is, in hindsight, a very obvious thing to do, this feedback loop has been not seen for 150 years, or let's say since the 1960s or so, since the days of NASA. And I think what is important here, the control theory way of looking at the problem that I tried to introduce you in the previous slide, which clearly shows you the direction that information, that perturbations propagate, that was decisive in discovering this effect. Now, what are the consequences? There are three things mentioned here. The first two are sort of technical. I'll skip that. One is thermoacoustic instability in an anechoic system. Now, traditionally, it was believed the flame has to sit in a resonator in order to go thermoacoustically unstable. But colleagues in Eindhoven discovered just by playing around with a low order model that that is not true. It seems that flames can develop instability even in an anechoic environment. And what you see here, that is the movie from the title slide, is a flame in an anechoic environment. The red line here on the top plot on the left and on the right, that shows the amplitude of the incoming waves reflected from the acoustics. So you can see, although we have considerable outgoing waves, these are the wiggly lines, our boundary conditions successfully eliminated all reflections. We have no incoming signal, and still this flame here develops very strong instability. Before we published that movie or that corresponding paper some 5 years ago, everybody would have said this is impossible. It cannot happen. You cannot have self-excited instability without feedback. And that is true, but the point is there is also intrinsic feedback. And other interesting effects then that we have discussed in a number of papers and other colleagues also since started investigating and looking at that. Anomalous response of eta modes, intrinsic thermoacoustic modes to reflection coefficient. Think back of the Millennium Bridge, where I said after the oscillations were first observed, additional dampers were installed. And in general, installing dampers is a good strategy to kill an instability because it eats up perturbation energy. So whatever energy you generate through the Rayleigh phenomenon, no pressure and heat release and expansion and so on and so forth, if you absorb that by a damper, the instability cannot grow in amplitude. Now the crazy or the anomalous thing about eta modes is these animals, they might prefer a situation where you decrease the reflection coefficient. It has been observed in experiment paper at the Combustion Symposium this year, the group of Qifei in China. They had an experiment where they showed for the first time also what we saw in simulation. Decreasing reflection coefficient can destabilize on one of these modes. The other one is the scaling. The frequencies do not behave as expected. Again, remember the flute. Opening, closing the holes on the flute changes the possible eigenfrequencies because effectively you change the length of the resonator. Eta modes don't behave like this. If you change the length of the resonator, if you change the temperature of the hot gas, which means the speed of sound, these modes often don't care. They are governed by the flow velocity from the flame holder to the flame. So they're convectively dominated. They show Struhal scaling and not Helmholtz scaling. And the last point I skipped because there are other things and I should come sometime soon also to an end. I have some 8 more minutes. Is that correct? Yeah, I think so. Huh? Okay, good. Now I told you all sorts of stuff about how dangerous thermoacoustic instabilities are and how unpleasant. Well, there is another kind of thermoacoustics, which is not combustion instability. So we use the thermoacoustic effect, interaction of unsteady heat release and acoustic waves, to either generate mechanical energy, so we have a thermoacoustic engine, or to have a refrigeration device. And this picture here is from the physics teacher of our school. He had a course for advanced pupils and had this homemade thermoacoustic engine constructed and analyzed. And here you also see a flame. What you have down here is a little heater. So you, oops, that was too quick, sorry. So here the flame is heated, but the point is the flame does not really take part in the thermoacoustic interaction loop. The flame does not exhibit any important unsteadiness. The flame is only there to generate a mean temperature gradient. And then the thermoacoustic effect is what you observe if you have a fluid element that is pushed back and forth by acoustics along a wall with a certain temperature gradient. Because here you can have a situation, imagine you have first a cold fluid parcel here that is compressed by the wave. It's an acoustic traveling wave in that case. It is first compressed by the acoustics, then it's, too fast again, then it's pushed to the right where the temperature of the wall is higher. So you have heat transfer from the wall to this compressed element. This heat transfer, of course, causes some expansion. And then the flame is pushed back again to the left. And then you have heat transfer from the element now back to the wall. So again, you have a cycle of compression and expansion synchronized in a suitable manner with addition and rejection of heat. And now think back to the PV diagram, this process can generate mechanical energy. And here I have a YouTube video, you can watch it yourself, a little thermoacoustic engine in operation. I hope this works also through, we don't have to watch the whole thing. The interesting starts about here, about 1 minute in.
There's a piston in the which you can just about see coming in and out of that metal plinth when it comes to the outside there. Little black piston appears and disappears. It's attached to a flywheel. And once we give it a kickstart, a bit like starting a car, it's going to revolve at a very fixed speed of about 2,700 RPM. There we go. There she goes, first time.
Okay, there she goes, as you said. Good man.
So this will revolve for as long as there's fuel in here. There's a little bit of meth spirit in there. And as long as it's providing heat to create this standing wave, the heat differential will make the motor continue to revolve.
Okay, so that is a thermoacoustic engine. They come in different flavors. They are discussed often in analogy to the Stirling engine. You don't need to have a flame to provide the heat that generates the gradient in the wall or in the stack, in the regenerator of the thermoacoustic engine. The heat could also come from solar in principle. Heat could be provided from geothermal sources. And two colleagues of mine, Chris Lawn from Queen Mary College in London, who is a combustion thermoacoustics person, and Guillaume Pinelet from the University of Le Mans in France. They wrote a paper a couple of years back where they discussed the commonalities and the differences between thermoacoustics of flames and thermoacoustics of engines. Because although the basic phenomena are the same, the importance of timing is of time lags or phase lags is crucial. The interaction of unsteady heat addition and rejection and interaction with acoustic and so on and so forth. The details are quite different. And interesting enough, also the two research communities hardly talk to each other and don't don't exchange a lot of methods and ideas. And this paper, review paper, as I said, gives you sort of a unified perspective, but also points out that there are dissimilar phenomena also in this game. So not everything here can be explained by the very same concepts. And so my last slide for today, further phenomenon related and relevant for both thermoacoustic engines and for thermoacoustic instabilities is the enhancement of heat transfer that results from strong flow oscillations. Now, that is often described as a main cause or main mechanism for damage. Maybe you remember the picture I showed you from the damaged rocket engines. It is often assumed, discussed in the literature, that the fluctuating flow that results from instability increases the heat load on the combustibles drastically, which eventually causes thermomechanical failure. Now, it was not so easy to reproduce this effect in large eddy simulation. That's what we tried here. So what you see is here over one cycle of oscillation, the normalized enhancement of heat transfer, so Nusselt number or heat transfer coefficient, over the value that you have in steady state. So if I have a modest oscillation amplitude, plus minus 40% of the mean flow value, this is turbulent channel flow. You see, okay, during part of the cycle, heat transfer is reduced. During part of the cycle, heat transfer is enhanced. But overall, the effect on average heat transfer is not very pronounced. Only if I go to rather large oscillation amplitudes. Now here we have 2.4. The oscillation amplitude is more than twice the amplitude of the mean flow, and 4.3 and 5.8 eventually. So only if I have very strong oscillation amplitude do I observe really a noticeable enhancement of heat transfer. Is it possible to have such strong oscillations? Yes, it is possible. Thermoacoustics can result in very significant oscillation amplitudes, so the pressure varies by order of magnitude of the operating pressure, and velocities oscillations are larger than mean flow velocity. So we do observe flow reversal during thermoacoustic instability. Interesting enough, we only observed this in our LES. We have not gotten around to really analyzing what is the fluid dynamic mechanism to cause these instabilities. Are there flow structures that form and separate? What is the exact phase relationship? Again, I'm sure also in this case, where you have an increase of average heat transfer, there must be a certain phase lag relation. Timing is everything between transport, convective of fluid particles along the wall and heat transfer into the fluid elements. Okay, that brings me to my last slide. Amazing enough, if your clock is right, this is a good timing. So this summary of my talk, I try to give you some idea what is the difference between a self-excited instability versus a resonance. This distinction, I have to admit, there are papers also in the thermoacoustic research community where this distinction is blurred. They speak of resonance when they should speak of self-excited instability. There are, that's also true, there are situations in combustion dynamics where resonance is also important. I try to convince you that timing is everything, also in instabilities, or in particular in instability. I told you, okay, high resolution LES, very challenging, lots of detailed insight, but in my opinion, you must always complement that with low order models. And one stronghold of what we've done is really bring these two worlds together. We construct from the LES low order or reduced order models of flame dynamics, for example, which we then stick into the low order models. So we have quantitatively accurate low order models also. I discussed the intrinsic thermoacoustic feedback. That is in principle, and in hindsight, a fairly obvious thing, but it is really, one of the reviewers of our papers wrote this once, a textbook changer, because for 50 years, nobody had this on their radar. And I showed you that it really gives rise to anomalous phenomena that we have to take into account into design of combustors. And I showed you thermoacoustics is not always bad. It can also be exploited to cool or to generate power. So thank you for your attention, and I'm open for questions.
Okay, thank you very much, Professor Polivka. It's a very interesting and inspiring presentation. I hope everybody could enjoy the presentation, and I believe there are still some, some questions directed to Professor Polivka. Well, I notice here that there is one question from Kalista Anjani or Rian. I don't know. Well, okay. The question is.
Yeah, I see it. Yes, it's.
Okay, you can see also. Well, okay.
Instability that you showed on the first slide, is it specific only for compressible gas, or has a similarity to other detachment of? You're referring to the animation on the title slide, I assume, and that would be only for compressible gas. Yes, there are hydrodynamic instabilities of flames also. A premix flame front can go unstable because there is a focusing effect of the streamlines. So this instability does not involve acoustics in an essential manner. The flame front can become wrinkling and start oscillating. You have interaction of displacement of the flame front and distortion of the shape of the flame front with vortices. And again, there is feedback. These distortions of the flame front generate more vortices, which further distort the flame. All this can be discussed in a sort of quasi-compressible limit where density depends on temperature, but density does not depend on pressure. So acoustics is not part of the picture. There are also thermodiffusive instabilities of flames. There are also instabilities like extinction, of course, another form of flame instability, if you like. Although extinction in practice is often accompanied by thermoacoustics, as you, for example, reduce fuel concentration as you lean a flame, often before it really blows out, you have a period where, for a short while, very intense oscillations occur, because in these very lean conditions, the flame becomes more susceptible to perturbations. So the feedback between the perturbations is strengthened, and instability may occur in this case. And detachment of gas from a gas core in gas liquid flow. I mean, I see some similarities with Richtmeier-Meshkov instabilities, detachment of a gas from, so you speak of annular flows in multiphase flows. It has similarity, I would think, in as much as these phenomena also are self-excited instabilities. Small perturbations can grow because they extract energy from a mean flow. The wavelengths and the frequencies you observe are often those that have the largest linear growth rate. So in that sense, rather abstract sense, there are similarities, but I don't see a very close similarity here. Okay, second question. Considering the thermoacoustic instability phenomena, what haven't been considered in the old boiler gas turbine design in the past, and what should be considered later in future design? Okay, I mean, perhaps first start, for a long time, thermoacoustic instability was not a significant issue for power generations, for gas turbines for power generation, because they have used diffusion flames. Diffusion flames are nice because they are quite robust. The fuel flames also generate lots of NOx, nitrous oxides. So that is not nice. And that's why the industry has switched to the lean premix combustion technology, and thereby could significantly reduce the emissions of nitrous oxides. But that also resulted in the problems with thermoacoustic instabilities across the board. All manufacturers have seen significant trouble, sometimes with significant cost because projects were late or installed machines were exhibiting problems in the field. And what has been done to fight these instabilities? Well, they could occur, for example, just by changing fuel. If you have a gas turbine that works fine in Switzerland and you bring it to Malaysia, the machine may exhibit instability because natural gas in Malaysia has a rather different composition, more higher hydrocarbons and so on and so forth. Even climate, humidity, temperature can trigger thermoacoustic instabilities that is stable in another regime. So the measures one takes is a mix of sometimes an educated operator just avoiding load regimes where the engine can go unstable. So there are certain ranges of power derating that you try to avoid. There are attempts to have burner staging, that not all the burners that fire into a single combustor receive the same amount of fuels. So not all the burners are marching in step. Some have a larger time lag, some have a smaller time lag, and thereby by breaking synchronicity, you can control instabilities. What you also can do is install dampers. That has been done quite successfully in the last case, and in the last decades, that you install Helmholtz resonators, or in rocket engines, quarter wave resonators. They usually log on to one specific frequency and can kill a mode at that one specific frequency, which sometimes has the unfortunate side effect that another mode then goes unstable. Now, there are many modes usually in a combustor. Usually one of them wins. If you kill that one mode, it's possible another mode starts acting up, so to speak. And for future design, there are ideas, for example, now with hydrogen combustion, the idea is we burn more and more hydrogen from renewable sources. And one then fairly obvious control approach could be that in a scenario where we add a bit of hydrogen to natural gas, we don't go 100% hydrogen right away. In that scenario, you can have different burners run at different power ratings or power contributions of hydrogen, or different ratios, hydrogen to methane or natural gas, basically. Again, changing the fuel time lags. Okay, next question here. I hope I, wait, Mr. or Dr. Siavali. I think one question disappeared up top of my screen. But the other question is, flames respond to acoustic changes as a result of expansion and compression of the fuels inside the combustion engine. The composition of fuels contributes. Yes, the composition of the fuels, as I indicated with hydrogen, it can change flame anchoring, flame stabilization. It can change chemical reaction times. Chemical reaction times are an effect of, or are part of the time lag. Composition of the fuels can change the burning velocity. And so burning velocity controls the flame shape. The flame length in particular, again, influences the time lag. Long flames have larger time lags. So I hope that answers the question. The flames respond to acoustic changes. Well, the combustion engine, I'm not sure I understand the question here, because the PV diagram where I said, hey, this is much the same as in a combustion engine. Of course, in a gas turbine, you don't have this pressure increase and decrease due to piston moving in cylinder. You have compression expansion because of the acoustic wave traveling across the fluid element. Okay, next question, can compressible heated gas without instability, without combustion, also experience thermoacoustic instability? Yes, there are interesting effects. The Sondhaus tube, it's also discussed briefly. If you have glass blowers, people who you have them, everything is industry now, but if you go to Venice, perhaps, and there are manufacturers for artifacts made of glass. And here you have people blowing into long pipes, where at the end of this long pipe, you have a bulb of melted glass, and they blow into it, and therefore a vessel is formed made of glasses. So, and here you can have a thermoacoustic instability, because in this long pipe, you have a temperature gradient, and you have obviously also a resonator with like a trombone with the glass bubble. And there is also similar effects in cryogenic applications. Taconis oscillations, they are called, when you have a huge temperature difference between a reservoir for liquid hydrogen, for example, or any liquid nitrogen. And you can also have a thermoacoustic instability developing in those systems. As far as I know, there are not significant damage effects to be. Maybe you have increased heat loss because of that, because basically this oscillation shuffles warmth, shuffles internal energy toward your cryogenic storage, which is of course undesired. The thermoacoustic instability in a gas chamber is a bad effect, that's true. Is there any method to suppress? I think I discussed quite a few, so maybe we skip that. Can the intrinsic feedback and feedback due to reflection as such cancel each other? Yes, that is exactly the point. Remember, I said the intrinsic instability often exhibits a stronger instability if you decrease reflection. So you're quite correct. The increase of reflection can kill the instability because they do cancel each other. They bring in extra phase relationships, and the response to the perturbation is no longer as cohesive and as phase aligned, and then it kills the instability. Okay, I think we're running out of time. Or is there?
Okay.
Maybe the law.
I think there is still one question left.
There is one, yeah.
Do you mind to answer it? Or even two?
I can.
Yeah, okay.
Yeah, I'll answer live this question on the standing and traveling wave. This is about thermoacoustic engines. And I showed you this interaction of heat transfer from a wall with temperature gradient and position. And there is a paper from the 80s, I think, separately. He argues that this interaction is possibly more efficient, can generate more mechanical energy if you have a traveling wave arrangement rather than a standing wave arrangement. And that's why in this picture here, bottom left, you would show the traveling wave, basically the flute or the combustion chamber linear arrangement. And here you have a traveling wave arrangement where a wave can travel in cycles in one direction around this loop. Again, these idealizations of the thermoacoustic process simply as a Stirling process is of course an approximation. But as far as I know, mind you, I'm not an expert in thermoacoustic devices. The traveling engine concept is more efficient. So, okay. Why do I use LES? Well, okay. I try to use for a long time RANs or unsteady RANs to capture flame dynamics. And I gave up some time in 2008, 2009. The point is you need a highly accurate combustion model, turbulent combustion model to get the flame dynamics right. And you have to resolve with high accuracy the temporal movement anyway. So yes, that is why we need LES. And also you're right, the large eddies can have a significant role. The eddies are formed by unsteady flow through an orifice. So you have accelerated flow vortex formation. And then these large eddies, which are resolved better in LES than in U-runs, is my experience, are important. How do we validate them? Well, we do the usual thing. Well, first of all, we don't invent our own turbulent combustion models, usually at least. Sometimes we do. But we rely a lot on the thickened flame model that was pioneered by Venant and Pinson, colleagues in France, that enjoys some credibility. Then we validate by comparing velocity fields, OH images of heat release. You can measure OH chemiluminescence in experiment and compare that with what you see as heat release in your large eddy simulation. And in the end, you can also look at stability limits and stability amplitudes. So LES is generally perceived in the community to give a faithful description of these phenomena. So thank you. Thank you for the interest in my talk.
Okay, thank you, Professor Polivka. It was a lively Q&A session. Yeah, it has attracted a lot of attentions from the audiences, and thank you very much. I hope it will be very useful for all of us. Well,
if there are further questions, send email or look on our website for ResearchGate. We have also a site which explains some of our projects, and we can find additional presentations and slides and papers also. Thank you.
Okay, you're welcome. Okay, I think it's time. The time is up, and before I conclude the sessions, let me once more thank Professor Polivka once more very much for your willingness to take part in this conference with the interesting presentation. And let me return the floor to the organizing committee. And thank you very much, and see you next time. Okay, thank you.
Okay. Thank you very much, Professor Harwin Sabtoadi, acting as moderator for this particular session. And also thank you very much to Professor Wolfgang Polivka for the presentation. It was a very interesting topic, and it was such a pleasure to listen to, Professor. Ladies and gentlemen, our agenda for today's session has been finished on the first day of the 2020 11th International Conference on Thermofluids. So on behalf of the committee, I would like to thank our esteemed keynote speakers. First of all, Professor Sutrisno from Universitas Gadjah Mada, Professor Graham Gus Nathan from the University of Adelaide, and Professor Wolfgang Polivka from TU Munich. Also, thank you for the paper presenters, and last but not least, our amazing moderators, Professor Samsul Kamal, Professor Harwin Sabtoadi, Mr. Tri Agung Rohmat, as well as Mr. Willy Prasida. We are looking forward to your participation tomorrow at the second day of the 11th International Conference on Thermofluid, consisting of keynote presentations from Associate Professor Muhammad Aziz from the University of Tokyo and Professor Nicholas Hutchins from the University of Melbourne. There will also be exciting and interesting paper presentations as well, and also an awarding session or an awarding ceremony for the best presentations. Once again, thank you very much, everyone, for the participation, and see you tomorrow on the second day of the 2020 11th International Conference on Thermofluid. Have a nice day, everyone. Thank you very much.
Yeah, thank you. Thank you. Hello.
Thank you very much. See you tomorrow.
Thank you. See you tomorrow.
See you tomorrow.